Welcome to Science for Sleep, a place where curiosity takes its time and every discovery becomes part of a gentle journey. Tonight, we'll discuss a fascinating discovery that brings us closer to answering the timeless question: are we alone in the universe? In 2016, a groundbreaking discovery was made, one that would spark a new era of exploration and reflection on the potential for life beyond Earth. Scientists revealed the existence of Proxima-B, an exoplanet orbiting the closest star to our Sun, Proxima Centauri. For decades, we've searched for Earth-like planets, wondering if we might one day find a world capable of supporting life. And with Proxima-B, we found a planet that, although distant, brings us one step closer to the answer. Proxima Centauri, the star that Proxima-B orbits, is located just over 4.2 light-years away in the constellation of Centaurus, making it the closest known star to our solar system. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. But it is still a part of the nearby cosmic neighborhood that we study so intently. Despite being relatively small, Proxima Centauri holds the distinction of being the closest neighbor to the Sun. The discovery of Proxima-B was a milestone in the search for exoplanets because it resides in the habitable zone of its star, sometimes referred to as the Goldilocks zone. This is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot and not too cold. The presence of liquid water is one of the key ingredients that scientists believe is necessary for life as we know it. The potential for liquid water on Proxima-B opened the door to the possibility of alien life, perhaps even microbial organisms thriving on its surface. But how exactly was Proxima-B discovered? The key to finding this distant world lay in the radial velocity method, a technique that has become a cornerstone of modern exoplanet discovery. This method involves measuring the wobble of a star caused by the gravitational pull of an orbiting planet. As a planet orbits its star, the planet's gravity tugs on the star ever so slightly, making the star appear to move in small, measurable ways. This subtle motion is detectable using spectrographs, instruments that can observe changes in a star's light spectrum. These shifts in light tell us a lot about the motion of the star and, by extension, the presence of planets around it. The team of scientists that made this discovery was using the HARPS spectrograph at the European Southern Observatory in Chile. In August 2016, they confirmed the presence of Proxima-B. It was a huge moment for astronomy, as the planet's proximity to Earth made it an ideal candidate for further observation. Proxima-B, with its potential for liquid water and its position in the habitable zone, became one of the most exciting targets for future study. But Proxima-B's discovery was not only significant because of its location in the habitable zone, it was also notable for the planet's size and mass. Proxima-B is about 1.3 times the mass of Earth, which places it in the category of super-Earths, planets that are more massive than our planet, but still capable of sustaining liquid water on their surfaces. This made Proxima-B one of the most promising candidates for the search for life beyond our solar system. Its relatively small size meant that it could have a similar surface gravity and atmospheric composition to Earth, further enhancing its potential to support life. As scientists turned their attention to Proxima-B, they also began to look at Proxima Centauri, the star it orbits. Proxima Centauri is a red dwarf star, and red dwarfs are known for being more active than stars like our Sun. They emit strong solar flares, bursts of radiation that can have significant effects on nearby planets. These flares are a major factor in determining whether a planet in the habitable zone can maintain an atmosphere conducive to life. While Proxima-B lies within the habitable zone of Proxima Centauri, Its proximity to a highly active star raises questions about the planet's atmosphere. Could it have an atmosphere that can shield it from the star's powerful radiation? Or is it vulnerable to the intense flares that are a hallmark of red dwarf stars? To answer these questions, scientists used computer simulations and other observational tools to explore the conditions on Proxima-B. They found that, while the planet is within the habitable zone, the frequent flaring of Proxima Centauri could potentially strip away a weaker atmosphere over time. However, they also found that if Proxima-B does have a strong magnetic field, it might have a protective shield against these stellar flares. The possibility of a protective magnetic field makes Proxima-B even more intriguing and suggests that future missions to the planet, should they ever be possible, will need to focus not only on its surface conditions, but also on its magnetic environment and atmosphere. The discovery of Proxima-B was part of a larger trend in the study of exoplanets. For years, scientists have been identifying and studying planets that exist outside of our solar system. With advances in technology, particularly the development of more powerful telescopes and spectrographs, we've been able to observe planets in greater detail than ever before. The discovery of Proxima-B is just one example of the kinds of planets we're finding. Planets that might one day be explored by future generations, whether through robotic probes or perhaps even human missions. The discovery of such a nearby planet opens up a new frontier in space exploration. But beyond the technicalities of the discovery, our Proxima-B represents something even deeper. A reminder of how much we have yet to discover about our universe. We now know that there are planets in our stellar neighborhood that might support life, and this discovery raises new possibilities for what we might one day encounter. The search for extraterrestrial life is no longer just an academic pursuit, but has become a fundamental part of humanity's quest to understand its place in the cosmos. As we continue to explore the stars, Proxima-B will remain one of the closest and most compelling objects in our search for answers. The excitement around Proxima-B is not just based on the possibility of life, but also on the larger implications for our understanding of the universe. For centuries, humans have looked up at the night sky and wondered if there were other worlds out there. With the discovery of Proxima-B, that wonder is no longer just speculation. It is grounded in the reality of scientific discovery and exploration. Looking ahead, the study of Proxima-B could help us learn more about the formation of planets and the conditions that make a world habitable. It could provide important clues about the origins of life and the possibility of life existing elsewhere in the universe. As we continue to develop the technology needed to study planets like Proxima-B, the mystery of whether life exists beyond Earth is one that will continue to captivate humanity's imagination. But no matter what we discover, one thing is clear. Proxima-B is a reminder that the universe is vast, and our search for understanding is just beginning. What makes Proxima-B special? Tonight, as we continue our journey, we will explore what makes Proxima-B such a fascinating and unique exoplanet. It's not just the proximity of its host star, Proxima Centauri, that draws our attention, but the possibility that this world might resemble our own in some profound ways. Proxima-B's characteristics suggest it could be a mirror of early Earth, a planet where conditions might be just right to support life as we know it. But what makes this discovery so compelling goes beyond just its location in the habitable zone of its star. We must delve into the planet's size, its orbit, and the mysteries that still lie hidden within its surface and atmosphere. Proxima-B is classified as a super-Earth, which means it is larger than our planet, but not quite as massive as giants like Neptune or Jupiter. Weighing in at about 1.3 times the mass of Earth, Proxima-B could offer a surface gravity similar to our own, depending on its composition. This gravitational pull plays an important role in determining the planet's ability to maintain an atmosphere, which is vital for the possibility of life. While the planet's mass places it firmly in the super-Earth category, it also means that Proxima-B could have a more substantial atmosphere than Earth, perhaps offering more protection from cosmic radiation and stellar flares. However, this remains a topic of active investigation, as scientists continue to study whether Proxima-B's atmosphere has survived the intense radiation from its star. The orbit of Proxima-B is another defining characteristic. The planet completes one full orbit around Proxima Centauri in just 11.2 Earth days, which means it is much closer to its star than Earth is to the Sun. Despite its proximity to Proxima Centauri, Proxima-B lies within the star's habitable zone, where temperatures could allow liquid water to exist, if conditions are right. The habitable zone, however, is not a one-size-fits-all concept. For Proxima-B, its closeness to Proxima Centauri means that it is constantly exposed to the star's stellar flares, which can be intense, unpredictable bursts of radiation. These flares could have significant implications for the planet's atmosphere and its potential for supporting life. Scientists believe that the star's flaring activity, combined with the planet's relatively short orbital period, could result in a tidally locked situation for Proxima-B. This means that one side of the planet would always face the star, experiencing perpetual daylight, while the other side would remain in constant darkness. This phenomenon is common among planets that orbit very close to their stars, as gravitational forces over time can cause the planet's rotation to sync up with its orbit. For Proxima-B, being tidally locked could have profound implications for the planet's weather patterns and the distribution of heat. The side facing the star would likely be much warmer than the side in shadow, creating extreme temperature gradients. However, if the planet has a sufficiently thick atmosphere, heat could potentially circulate between the two sides, mitigating some of the extreme temperature differences. While the possibility of tidal locking is fascinating, scientists also recognize that it could create significant challenges for any potential life on the planet. Without a day-night cycle, the conditions on Proxima-B would be radically different from those on Earth. However, it's also possible that the planet has a more complex atmospheric system that allows for the redistribution of energy, similar to how weather systems work on Earth. This means that even with tidal locking, Proxima-B could have a more stable and habitable environment than we might expect. Another key feature of Proxima-B is its potential for liquid water. Liquid water is considered one of the most important ingredients for life, and the presence of liquid water on Proxima-B would increase the likelihood that life could exist there. Proxima-B is located in the habitable zone of its star, which means that, in theory, the conditions on the planet could support liquid water on its surface. But the situation is more complex than simply being in the habitable zone. The planet's atmosphere and its interaction with Proxima Centauri's radiation play a crucial role in determining whether water could remain liquid on the surface. The atmospheric composition of Proxima-B is still unknown, but it is a key focus for scientists studying the planet. Proxima-B's atmosphere, if it exists, could protect the planet from harmful radiation and regulate temperatures. However, the planet's exposure to Proxima Centauri's flares complicates this. The star's frequent outbursts of radiation could strip away the atmosphere over time, leaving the planet exposed to the harsh conditions of space. Some scientists hypothesize that Proxima-B might have a thick carbon dioxide-rich atmosphere, similar to Venus, which could create a greenhouse effect that raises temperatures to the point where liquid water could exist, despite the planet's proximity to its star. But this theory remains speculative, and scientists are actively working to gather more data to confirm or rule out this possibility. The challenge of studying Proxima-B lies in its distance from Earth and the limitations of current technology. While it is the closest known exoplanet in the habitable zone, it is still over 4 light-years away, which means that we can't yet send spacecraft to study it directly. However, with advancements in technology, particularly the launch of the James Webb Space Telescope, we may soon be able to gather more detailed information about Proxima-B's atmosphere, surface, and potential for life. The James Webb Space Telescope, set to launch in the coming years, will allow scientists to study the planet in unprecedented detail, looking for chemical signatures in the atmosphere that could indicate the presence of life. In the meantime, scientists are using computer simulations and observations of other exoplanets to try to better understand the potential conditions on Proxima-B. These simulations help us to model how the planet's atmosphere might behave, how its climate might work, and whether conditions could be conducive to life. The combination of spectroscopic data, simulated models, and future observations will continue to shape our understanding of Proxima-B in the years to come. Each new piece of information brings us closer to the possibility of one day answering the question, could life exist on Proxima-B? As we contemplate the possibility of life on Proxima-B, it is important to remember that the planet's discovery is just one step in the ongoing exploration of the cosmos. Proxima-B is a symbol of our growing curiosity about the universe and our place within it. The discovery of this nearby world brings us one step closer to understanding the broader picture of exoplanetary systems. And it challenges us to think more deeply about the potential for life elsewhere in the universe. In a way, Proxima-B stands as a reminder of the vastness of space and the uncharted territories that await us in the exploration of the stars. In the next part of our journey, we will look at the star that hosts Proxima-B, Proxima Centauri, and how its unique characteristics shape the environment of its orbiting planet. Proxima Centauri is not only the closest star to our Sun, but it also plays a pivotal role in determining the conditions on Proxima-B. The characteristics of Proxima Centauri. As we venture deeper into the story of Proxima-B, we must pause to consider the star that sustains its orbit. Proxima Centauri. This small red dwarf star lies just over 4.2 light-years away from Earth, making it the closest stellar neighbor to our Sun. While it may seem like a humble star, Proxima Centauri plays a crucial role in shaping the environment of its planets, including Proxima-B. Proxima Centauri is a red dwarf, a type of star that is much smaller, cooler, and dimmer than our Sun. It has only about 12% of the mass of the Sun and is approximately 1/200th as bright. This lower brightness is a defining feature of red dwarfs, and it has a profound effect on the planets that orbit them. For instance, Proxima-B's habitable zone, the region where conditions could allow liquid water to exist, is much closer to the star than Earth's habitable zone is to the Sun. This is because Proxima Centauri, being cooler and less luminous, requires a much closer distance for its planets to receive the same amount of energy and warmth that Earth gets from the Sun. Proxima Centauri is part of a triple star system. It is gravitationally bound to 2 other stars, Alpha Centauri A and Alpha Centauri B, which are much larger and more luminous than Proxima Centauri. However, Proxima Centauri is the closest of the 3 stars to us, and it is also the smallest. The proximity of these stars has a significant impact on the dynamics of the system, with their gravitational interactions influencing the orbits of planets like Proxima-B. One of the most interesting aspects of red dwarf stars like Proxima Centauri is their stellar flares. These violent bursts of energy can release vast amounts of radiation into space, and Proxima Centauri is known for its frequent flaring activity. While our sun also experiences solar flares, red dwarfs are much more active. Some red dwarfs, including Proxima Centauri, can experience flares that are hundreds or even thousands of times more powerful than the strongest solar flares from our sun. These flares can have a profound effect on the planets that orbit these stars, especially if the planets are located in the star's habitable zone. For Proxima-B, the frequent flares from Proxima Centauri present both challenges and opportunities. On the one hand, these flares could strip away a weaker atmosphere, making it difficult for the planet to retain water or protect any potential life forms. On the other hand, if Proxima-B has a strong magnetic field, they could provide some protection against these intense bursts of radiation. A magnetic field acts like a shield, deflecting charged particles and preventing them from reaching the surface of the planet. This shield could make all the difference in determining whether Proxima-B can support life. In addition to its flaring activity, Proxima Centauri's age and longevity are also important factors in understanding the planet's potential for habitability. Red dwarfs like Proxima Centauri have long lifespans, often lasting tens of billions of years, far longer than stars like our sun. This extended lifetime means that planets in orbit around red dwarfs have more time to develop life if the conditions are right. Proxima Centauri is estimated to be around 4.85 billion years old, and it is expected to continue burning hydrogen in its core for many billions of years to come. This provides ample time for Proxima-B and any potential life on it to evolve. The activity level of Proxima Centauri is an essential factor in understanding how it influences its planets. As mentioned, red dwarfs are known for their flare activity, which can vary greatly over time. Some red dwarfs experience periods of intense flaring, while others remain relatively quiet. For Proxima-B, understanding the pattern of flares from its star is crucial for determining its habitability. If the flares are constant and intense, they could make it difficult for life to thrive. However, if the flaring activity is more intermittent, there could be periods of calm where the planet is able to maintain a more stable environment. One important question that scientists are working to answer is whether Proxima-B's atmosphere, if it has one, is being eroded by these powerful flares. While Earth's atmosphere is protected from solar flares by our planet's magnetic field, Proxima-B's magnetic field, if it exists, could play a similar role in shielding the planet from the effects of the star's flares. It's possible that, with a strong enough magnetic field, Proxima-B could retain a thick atmosphere and protect its surface from the harmful radiation of Proxima Centauri. However, without such a magnetic field, the planet's atmosphere could be gradually stripped away by the star's radiation, making it much harder for liquid water to remain on the surface. To learn more about Proxima Centauri's flaring behavior and its effects on Proxima-B, scientists are using a variety of tools and methods. Space telescopes like the Hubble Space Telescope and the James Webb Space Telescope are being used to observe Proxima Centauri and its activity in greater detail. By studying the star's flares and the radiation it produces, scientists can learn more about the conditions on Proxima-B and whether they are suitable for life. Additionally, radio telescopes are being used to monitor the star's activity across different wavelengths, helping to provide a more comprehensive picture of the star's behavior. As we move forward, the study of Proxima Centauri will continue to be a central focus for astronomers interested in the possibility of life on Proxima-B. The star's flares, its age, and its proximity to our solar system make it an intriguing target for exploration. In the future, spacecraft could be sent to observe Proxima Centauri and its planets in even greater detail, providing us with a better understanding of the conditions that shape the environments of exoplanets. Effects of Proxima Centauri's flares on Proxima-B. As we continue to explore the relationship between Proxima Centauri and its orbiting planet Proxima-B, we find ourselves drawn to one of the most significant challenges to habitability on this distant world: the effect of stellar flares. Are these intense bursts of energy emitted by red dwarf stars like Proxima Centauri can have a profound impact on any planets in their vicinity, and Proxima-B is no exception. Proxima Centauri, as we've discussed, is known for its frequent stellar flares, which are explosive outbursts of radiation and charged particles. These flares can release energy that is up to 100 times more powerful than the most intense solar flares our Sun produces. For planets like Proxima-B, which lies relatively close to its host star, these flares could present a significant challenge for the development and sustainability of life. Understanding the potential consequences of these flares is essential for determining whether Proxima-B could truly support life. The intensity of Proxima Centauri's flares raises several questions. Could these bursts of radiation be enough to strip away Proxima-B's atmosphere, leaving it exposed to the harsh conditions of space? Could they prevent the planet from maintaining liquid water on its surface, thereby hindering the possibility of life? To answer these questions, scientists have turned to computer simulations and observational data to model the effects of stellar flares on planets like Proxima-B. One of the primary concerns is how these flares might affect the atmosphere of Proxima-B. Our Earth is protected from the Sun's flares by our planet's magnetic field, which acts as a shield, diverting harmful radiation away from our atmosphere. Without such a protective magnetic field, planets orbiting red dwarf stars like Proxima Centauri might not be so fortunate. If Proxima-B lacks a strong magnetic field, it could face the risk of its atmosphere being gradually stripped away by the star's intense radiation. This would make it much more difficult for the planet to retain liquid water, as the atmosphere would be unable to regulate temperature and protect the surface from extreme conditions. But it's not all bad news for Proxima-B. While the intense flaring from Proxima Centauri presents a challenge, it's possible that the planet could still maintain an atmosphere capable of supporting life. If it has a strong magnetic field, magnetic fields act like protective shields, deflecting charged particles and cosmic radiation away from a planet's surface. If Proxima-B has a magnetic field strong enough to shield it from the star's radiation, it could maintain a thick atmosphere capable of sustaining liquid water. For such a magnetic field would be key to protecting the planet from the harmful effects of Proxima Centauri's frequent flares. Scientists are currently studying how magnetic fields work on exoplanets like Proxima-B. We know that our own Earth's magnetic field is generated by the motion of molten iron in our planet's core, and we suspect that other planets with similar conditions could have magnetic fields as well. If Proxima-B has a molten core and a similar magnetic dynamo mechanism, it might be able to generate a protective magnetic field of its own. However, whether Proxima-B's magnetic field, if it exists, is strong enough to protect the planet from the radiation of Proxima Centauri is still a matter of debate. In addition to its magnetic field, and Proxima-B's distance from its star is another factor that could influence how much radiation it receives. Proxima-B orbits its star at a distance of just 0.0485 astronomical units, AU, which is much closer than Earth is to the Sun. While this close proximity places the planet in the star's habitable zone, it also means that Proxima-B is subject to the star's flares much more frequently than Earth is to the Sun's flares. As a result, the planet could experience periods of intense radiation that could disrupt the stability of any atmosphere and potentially make the surface uninhabitable for long periods of time. Despite these challenges, there is still hope for Proxima-B's habitability. Computer models suggest that even with the risk of atmospheric stripping due to stellar flares, Proxima-B could still retain a sufficiently thick atmosphere if it is able to generate enough volcanic activity or other geological processes to replenish its atmosphere over time. Volcanic eruptions can release gases like carbon dioxide and water vapor, which contribute to the thickening of a planet's atmosphere and help regulate surface temperatures. If Proxima-B has an active geological system, this process could potentially sustain an atmosphere capable of supporting life. In addition, scientists are studying how space weather could affect planets like Proxima-B. Some researchers suggest that the star's radiation might not necessarily strip away the entire atmosphere, but could instead create a layer of protection around the planet. This protective layer would act like a kind of shield, helping to preserve the planet's atmosphere and allow for the presence of liquid water on the surface. While much remains to be discovered about the precise conditions on Proxima-B, the potential for life remains a compelling possibility. As scientists continue to study the star and its planets, they are learning more about the long-term impacts of stellar flares on the habitability of planets in red dwarf systems. Proxima-B's close proximity to Proxima Centauri makes it a unique target for observation, and future space missions may one day help us better understand how this planet is affected by the flaring activity of its star. The search for alien life is one of the most profound quests in modern science, and Proxima-B stands as a symbol of humanity's growing curiosity about the cosmos. While the flaring activity of Proxima Centauri presents challenges, it also provides us with an opportunity to explore how life might survive and thrive in extreme environments. Whether Proxima-B can support life or not, the ongoing study of this distant world will deepen our understanding of the conditions required for life to exist beyond Earth. As we continue this journey, we'll explore the planet's atmosphere further, considering whether it could support life or if Proxima-B's environment is simply too harsh to sustain anything more than the most resilient forms of life. We'll also look at the future of space exploration and what role Proxima-B might play in the ongoing search for planets that resemble our own surface and climate as we continue to explore the potential for life on Proxima-B. And it's time to turn our attention to what the planet's surface and climate might be like. Proxima-B, as we've already established, is located within the habitable zone of its star, Proxima Centauri, where conditions might allow for liquid water to exist. However, understanding the exact climate and surface conditions of Proxima-B is crucial in determining whether this planet could actually sustain life. First, let's consider the surface conditions. Proxima-B is thought to be a rocky planet, much like Earth, with a surface that could potentially support features like mountains, valleys, and oceans. The planet is 1.3 times the mass of Earth, which suggests that it has a similar density and composition. It is likely that Proxima-B's surface is made up of rocky material and could even feature tectonic activity, similar to what we observe on Earth. However, given the planet's close proximity to its star, we also need to consider the effects of radiation and stellar flares on its surface. Proxima-B's surface is likely subject to extreme temperature variations. If the planet is indeed tidally locked, which is a possibility due to its proximity to Proxima Centauri, one side of the planet would always face the star, while the other side would be in constant darkness. This means that the day side of Proxima-B would experience constant sunlight, potentially making it much hotter than Earth's equator. The night side, on the other hand, would be perpetually dark and much colder, with temperatures potentially plummeting to extreme lows. If Proxima-B is not tidally locked, and it would still experience extreme temperature differences due to its close orbit around Proxima Centauri. Even if the planet has a more Earth-like day-night cycle, the proximity to the star means that the day side of the planet would still be exposed to intense radiation and heat. This could create a climate where extreme weather patterns dominate, with high winds and fluctuating temperatures. The existence of liquid water on Proxima-B's surface is still a subject of debate among scientists. Water is essential for life, and if Proxima-B does have water, it would likely be concentrated in oceans, lakes, or rivers. However, the intense radiation from Proxima Centauri could potentially evaporate any surface water on the planet, especially on the side that faces the star. On the dark side of the planet, water could remain frozen, thus creating vast, icy landscapes. These extreme contrasts in temperature between the day and night sides of Proxima-B could result in the formation of huge weather systems, with massive storms that could sweep across the planet. Despite these challenges, there is still a possibility that Proxima-B could have a stable climate if certain conditions are met. One key factor would be the presence of a thick atmosphere that could help regulate temperatures and create a more moderate climate. If the planet has an atmosphere rich in carbon dioxide, water vapor, or other greenhouse gases, it could act like a thermal blanket, trapping heat and preventing the planet from cooling too drastically. This would allow for a more stable environment where liquid water could exist, even in the face of extreme temperature fluctuations. Computer simulations are helping scientists model what the climate of Proxima-B might be like. By inputting various factors, such as the planet's distance from Proxima Centauri, its orbital period, and the composition of its atmosphere, researchers can generate predictions about the planet's surface and climate. These simulations suggest that if Proxima-B does have a thick atmosphere, it might be able to moderate the temperatures enough to allow for liquid water, especially if the planet has active weather systems that help distribute heat around the planet. Another important consideration is whether Proxima-B has oceans or lakes that could support life. If Proxima-B is able to retain water on its surface, these bodies of water could provide a habitat for microbial life, or perhaps even more complex forms of life. Just as life on Earth began in the oceans, it is possible that Proxima-B's oceans could serve as a cradle for life to evolve. However, the presence of water alone does not guarantee that life could emerge. The conditions in these oceans, such as temperature, acidity, and chemical composition, would need to be just right for life to take hold. The possibility of subsurface oceans is also a topic of interest for scientists studying Proxima-B. Some researchers believe that, even if the surface of the planet is inhospitable due to the planet's exposure to Proxima Centauri's flares, life might still be able to exist beneath the surface. Similar to Europa, one of Jupiter's moons, Proxima-B could have a subsurface ocean beneath its icy crust, where life could thrive in dark, pressurized environments. The heat generated by the planet's geothermal activity, or tidal forces from its orbit around Proxima Centauri, could keep these oceans warm, creating an environment that is suitable for life. If Proxima-B does have subsurface oceans, it could have a very different kind of ecosystem than what we are familiar with on Earth. Without sunlight, life in these oceans would need to rely on chemical energy rather than photosynthesis. In similar environments on Earth, such as at hydrothermal vents on the ocean floor, scientists have discovered thriving ecosystems of microbes that rely on chemicals like sulfur and methane to survive. It is possible that Proxima-B could harbor similar ecosystems, living off the chemical energy that emanates from its planet or star. The tectonic activity on Proxima-B is another factor that could influence the climate and surface conditions of the planet. If the planet has an active core, like Earth's, it could experience volcanic eruptions, which would release gases into the atmosphere and potentially contribute to a greenhouse effect. This process could help regulate the planet's temperature and maintain a habitable environment, similar to how Earth's volcanoes have helped to create and maintain its atmosphere over billions of years. The presence of volcanic activity could also make the planet more geologically active, potentially leading to the formation of mountain ranges valleys, and other features that are characteristic of Earth's surface. As we look to the future, the study of Proxima-B's surface and climate will continue to be a critical area of focus for astronomers and planetary scientists. By observing the planet's atmosphere, studying its orbital dynamics, and using advanced simulations, scientists hope to answer some of the most important questions about Proxima-B's potential for habitability. Can it support liquid water? Does it have a stable climate? And, most importantly, could life emerge on this distant world? In the next segment, we will look at Proxima-B's potential atmosphere and whether it could protect the planet from the intense radiation of its star. We will also explore how scientists are studying this exoplanet using advanced telescopes and spacecraft to learn more about its surface and climate. So the answers we uncover will bring us closer to understanding whether Proxima-B could truly be another Earth-like world in our cosmic neighborhood. The possibility of water and life. As we continue our exploration of Proxima-B, one of the most exciting aspects of this exoplanet is the potential for liquid water. Water, as we know, is a fundamental building block for life, and its presence on Proxima-B opens up fascinating possibilities. Could this distant planet, orbiting a small and dim star just 4.2 light-years away from Earth, host life as we know it? Or at the very least, could it support the conditions necessary for life to take hold? This question has captured the imaginations of scientists, astronomers, and dreamers alike. And it's a key factor in determining whether Proxima-B could be a true sister world to Earth. First, let's consider why water is so important in the search for life. Life on Earth, as we know it, evolved in water. From the oceans that cover most of our planet's surface to the rivers, lakes, and even the smallest droplets in the atmosphere. Water is crucial for the chemical reactions that sustain life. Whether it's the hydrological cycle or the way water helps to regulate temperatures, water plays an integral role in the balance of our biosphere. Thus, the discovery of water on other planets is seen as one of the strongest indicators that life might be possible elsewhere in the universe. So, what about Proxima-B? This exoplanet lies within the habitable zone of its star, Proxima Centauri, meaning it's at the right distance for liquid water to potentially exist. For a planet to maintain liquid water on its surface, it must be at just the right distance from its star, not too close, where the water would boil away, and not too far, where it would freeze. Proxima-B falls within the sweet spot, where temperatures could, in theory, allow for liquid water to persist. This, in itself, is a promising sign. However, just because a planet resides in the habitable zone does not guarantee that water will actually exist on its surface. Proxima-B's climate and atmospheric conditions are essential factors in determining whether water can remain liquid. For water to stay in a liquid state, the planet needs to have a stable atmosphere that can regulate temperature, pressure, and humidity. Proxima-B's close orbit around Proxima Centauri, its rapid 11.2-day orbit, also means that it may be tidally locked. No, with one side always facing the star and the other in eternal darkness. This could create extreme temperature differences between the two sides of the planet. On the day side, temperatures could rise to scorching levels, while the night side could plunge into freezing cold. In this extreme scenario, how can water remain liquid? If Proxima-B has a thick atmosphere, it could potentially distribute heat across the planet, in much the same way that Earth's atmosphere helps to moderate temperatures. A thick atmosphere on Proxima-B could allow for heat transfer from the hot, sun-facing side to the cold, dark side. This heat redistribution might help to stabilize temperatures and prevent the freezing or evaporation of water. For example, a thick atmosphere filled with carbon dioxide could create a greenhouse effect on trapping heat and raising temperatures enough to keep water in a liquid state. In this case, water vapor might even form clouds and precipitation, leading to weather patterns that could further help regulate the planet's temperature. Of course, the presence of water vapor and the potential for precipitation depend on the planet's ability to retain a stable atmosphere. If Proxima B's atmosphere is too thin or is stripped away by the intense radiation from its host star, any water on the surface would either evaporate or freeze. The star's stellar flares, which are much more intense than the flares produced by our sun, could further erode the atmosphere over time. These frequent bursts of radiation can heat up the atmosphere and, in extreme cases, might blow it away entirely. For Proxima B to retain its atmosphere and liquid water, it would need to either have a robust magnetic field or an atmosphere thick enough to resist the effects of the flares. One possible solution to this problem is that Proxima B could have a strong magnetic field, much like Earth. A magnetic field would act as a shield, protecting the planet from the harmful effects of radiation. This magnetic protection would be particularly important, given the fact that Proxima Centauri is an active red dwarf, prone to frequent and intense flares. The presence of a magnetic field could also help preserve the atmosphere, preventing it from being stripped away by the star's radiation. While we don't yet know whether Proxima B has a magnetic field, it's an important factor that could make a huge difference in the planet's potential for habitability. In addition to the atmosphere and magnetic field, another important factor is geological activity. On Earth, tectonic activity, such as volcanism and plate tectonics, plays a vital role in regulating the climate and maintaining the planet's habitability. Volcanoes release gases like carbon dioxide, which help to maintain the greenhouse effect and regulate temperatures. If Proxima B has an active geological system, it could continually replenish its atmosphere with gases that help to trap heat and maintain a stable environment. This process, known as the carbon cycle, is crucial for maintaining the conditions necessary for liquid water to exist on the surface. In the case of Proxima B, volcanic activity could also create local hotspots where life might thrive. Just as deep-sea hydrothermal vents on Earth support unique ecosystems, Proxima B could have subsurface hot springs or geothermal areas where microbial life could exist, protected from the radiation and extreme surface temperatures. These potential ecosystems would rely on chemical energy rather than sunlight for survival, much like life at Earth's hydrothermal vents. This idea raises the possibility that life on Proxima B could exist in forms very different from what we find on Earth, relying on chemical processes rather than photosynthesis. The existence of subsurface oceans is another intriguing possibility. Even if the surface of Proxima B is inhospitable, it's possible that the planet has liquid water beneath its frozen crust. This is similar to the way that moons like Europa and Enceladus in our solar system are believed to have subsurface oceans beneath their icy surfaces. If Proxima B has a layer of ice covering a liquid ocean, the heat from the planet's core or from tidal forces caused by its orbit around Proxima Centauri could keep the water beneath the ice warm enough to support life. These subsurface oceans would be shielded from the harmful radiation from the star and could harbor microbial life that relies on chemical processes rather than sunlight. The Earth similarities. As we continue our exploration of Proxima B, it's time to take a closer look at what makes this distant world so intriguing: its similarities to Earth. When astronomers discovered Proxima B, one of the most exciting aspects of the planet was how it compared to our own Earth. While Proxima B is located in a completely different star system, it possesses certain characteristics that remind us of our own planet, making it one of the most promising candidates in the search for Earth-like exoplanets. First, Let's examine Proxima-B's size. With a mass that is approximately 1.3 times the mass of Earth, Proxima-B is classified as a super-Earth, a type of exoplanet that is larger than Earth but still within a size range that could support life. Proxima-B's mass places it in the category of planets that are potentially able to retain an atmosphere similar to Earth's, as they have a gravity strong enough to hold gases and prevent them from escaping into space. This is a crucial factor in determining whether a planet could support life, as a strong gravitational pull allows for the presence of an atmosphere that can regulate temperature and create stable conditions on the surface. While Proxima-B is larger than Earth, it is not an enormous gas giant like Jupiter or Saturn. Instead, it is a rocky planet, similar to Earth in its composition. This means that Proxima-B likely has a solid surface made of rocky materials, just like Earth. Scientists have inferred this based on the planet's mass and the fact that it orbits within the habitable zone of its star. The fact that Proxima-B is a rocky planet increases its potential for hosting life, as rocky planets are more likely to have stable surfaces where water could exist in liquid form, a key ingredient for life. Proxima-B's gravity is another point of comparison with Earth. While the exact value of Proxima-B's gravity is still under investigation, scientists estimate that it is only slightly stronger than Earth's. The planet's gravity, being 1.3 times that of Earth, would likely allow for a surface environment that is similar to Earth in many ways. This is important because gravity plays a role in how a planet retains an atmosphere and supports liquid water. Stronger gravity helps hold onto gases like oxygen and nitrogen, which are essential for life on Earth. So, just as gravity shapes the way life thrives on our planet, Proxima-B's gravity could provide the necessary conditions for a stable, breathable atmosphere. The most significant similarity between Proxima-B and Earth is that both planets are located in the habitable zone of their respective stars. For Earth, the habitable zone is the distance from the Sun, where temperatures are just right for liquid water to exist. Proxima-B orbits within the habitable zone of Proxima Centauri, a red dwarf star, which means that the planet is at the right distance to potentially support liquid water on its surface. This zone is also called the Goldilocks zone because it is not too hot and not too cold, but just right for life to exist. While the concept of the habitable zone is fundamental in the search for life beyond Earth, it is important to note that being in the habitable zone doesn't automatically guarantee that a planet can support life. Many factors contribute to a planet's ability to maintain life-sustaining conditions, including its atmosphere, surface temperature, and magnetic field. But Proxima-B's location in the habitable zone certainly makes it an intriguing candidate for further study. The orbital characteristics of Proxima-B also bring it closer to Earth. As mentioned earlier, the planet completes one full orbit around Proxima Centauri in just 11.2 Earth days, which is much shorter than Earth's orbital period of 365 days. This fast orbit suggests that Proxima-B is very close to its star. Despite its proximity, the planet is in the habitable zone, and scientists believe it could maintain surface temperatures suitable for liquid water. However, the fact that it is so close to its star means that Proxima-B might be tidally locked, with one side of the planet always facing the star and the other side in eternal darkness. Being tidally locked means that one side of the planet would experience constant daylight, and the other side would be in perpetual darkness. This would create an extreme temperature difference between the two sides. The day side would likely be much warmer, while the night side would be incredibly cold. While this presents a challenge to habitability, it is not necessarily a barrier to life. If Proxima-B has a thick atmosphere that can redistribute heat, it might be able to maintain more moderate temperatures across the planet's surface. Atmospheric circulation could help transfer heat from the day side to the night side, creating a more stable environment. In many ways, Proxima-B's orbit mirrors that of Earth's early years, when the planet was first forming and undergoing dramatic changes in temperature and conditions. Just as Earth has developed a balanced climate through the interplay of its atmosphere, ocean currents, and weather systems, Proxima-B could develop similar systems that help regulate its surface temperature and create a stable environment for life to evolve. If Proxima-B has the right atmospheric composition and geological activity, the planet could maintain the delicate balance needed for liquid water to remain on its surface. The potential for life on Proxima-B is further enhanced by the planet's orbital resonance with Proxima Centauri. This resonance means that the gravitational interactions between the planet and its star could help maintain the planet's stability over long periods of time. Just as Earth's orbit is stable and predictable, Proxima-B's orbit could also remain stable, which would contribute to the long-term habitability of the planet. The orbital dynamics of the system suggest that Proxima-B could experience periodic changes in climate, but these changes would be gradual enough to allow for the adaptation of life forms over time. While Proxima-B's similarities to Earth are striking, it's important to remember that this exoplanet also has its differences. Proxima Centauri, the star that Proxima-B orbits, is a red dwarf, which is much cooler and less luminous than our Sun. This affects the size and shape of the habitable zone, as we discussed earlier. Proxima-B's close orbit around its star means that the planet is subjected to different conditions than Earth, especially when it comes to the intensity of radiation from the star. Proxima Centauri is known for its stellar flares, which can be hundreds of times more intense than the flares produced by our Sun. These flares could present a significant challenge to the habitability of Proxima-B, especially if the planet lacks a strong magnetic field to protect it from the star's radiation. The Earth differences. As we've explored in the previous sections, Proxima-B shares many characteristics with Earth, from its rocky composition to its potential for liquid water. However, Proxima-B is far from an exact twin of our home planet. In fact, there are significant differences between Proxima-B and Earth that raise important questions about the planet's ability to support life as we know it. These differences largely stem from the fact that Proxima-B orbits a red dwarf star, Proxima Centauri, which is fundamentally different from our Sun in terms of size, luminosity, and stellar activity. One of the most striking differences between Proxima-B and Earth is the distance between the planet and its star. While Earth orbits the Sun at a distance of about 93 million miles, 1 astronomical unit, Proxima-B is much closer to its host star, located at a mere 0.0485 astronomical units from Proxima Centauri. This proximity means that Proxima-B completes one full orbit around its star in just 11.2 Earth days, a stark contrast to Earth's 365-day orbit. While this rapid orbit places Proxima-B in the habitable zone of its star, where temperatures could theoretically allow for liquid water, it also presents challenges. Proxima-B's close distance to its star means that it is likely tidally locked, with one side always facing the star, while the other side remains in perpetual darkness. Tidal locking, the perpetual day and night. If Proxima-B is indeed tidally locked, as scientists suspect, it would mean that one hemisphere of the planet is constantly bathed in sunlight, while the other is shrouded in eternal night. The side facing the star would experience constant daytime, while the opposite side would endure constant darkness. This tidal locking creates a dramatic temperature gradient across the planet's surface, with the day side becoming incredibly hot and the night side becoming frigidly cold. This extreme temperature difference between the two hemispheres could present a serious challenge for the potential habitability of Proxima-B. Without the moderating effects of seasons or a day-night cycle, the planet's surface would be subjected to harsh and unrelenting conditions. On the day side, temperatures could soar, potentially reaching the boiling point of water. On the night side, temperatures could plummet to sub-zero levels, causing water to freeze. The presence of liquid water on Proxima-B would depend on the planet's atmosphere and the ability of its climate system to distribute heat between the day and night sides. However, all is not lost for Proxima-B. While tidal locking creates challenges, it also presents opportunities for the planet to maintain a more stable climate if it has the right atmospheric composition. If Proxima-B has a thick atmosphere, heat could be redistributed from the hot day side to the cold night side, potentially creating more even temperatures across the planet. Atmospheric circulation, driven by the rotation of the planet and the energy from the star, could help regulate the temperature and prevent extreme heat and cold. This type of atmospheric behavior is similar to how Earth's atmosphere helps distribute heat from the equator to the poles, creating a more temperate environment. Additionally, if Proxima-B has an active weather system, such as winds, clouds, and precipitation, it could help further moderate temperatures and create more Earth-like conditions. These weather systems could transport heat and moisture across the planet, preventing the day side from becoming too hot and the night side from becoming too cold. The presence of clouds could also provide some protection from the intense radiation of Proxima Centauri, reflecting some of the energy away from the surface and helping to maintain a more stable climate. Stellar flares, a barrier to habitability. Another key difference between Proxima-B and Earth is the stellar activity of Proxima Centauri. Unlike our Sun, which has relatively predictable solar cycles, red dwarf stars like Proxima Centauri are known for their extreme flaring behavior. These flares can release intense bursts of radiation that can strip away a planet's atmosphere, especially if the planet is located close to the star, as Proxima-B is. These flares can be hundreds of times more powerful than the solar flares we observe on Earth. And they could pose a significant threat to Proxima-B's ability to maintain a stable atmosphere and support life. While Earth experiences solar flares, our planet's magnetic field acts as a protective shield, deflecting charged particles and protecting our atmosphere from being stripped away. However, it remains unclear whether Proxima-B has a similar magnetic field that could protect it from the powerful flares of Proxima Centauri. Without such protection, Proxima-B could face significant challenges in maintaining its atmosphere, which is crucial for supporting liquid water and life. The frequency and intensity of Proxima Centauri's flares make it an even more challenging environment for life. If the flares are frequent and powerful enough, they could prevent the planet from having a stable climate, making it difficult for life to evolve or survive. While Proxima-B is located in the habitable zone of its star, its proximity to an active red dwarf raises the question of whether it could truly maintain the conditions needed for life. Proxima-B's atmosphere, a key to life. In light of the challenges posed by Proxima Centauri's stellar activity, the atmosphere of Proxima-B becomes even more important. A strong atmosphere could protect the planet from the harmful effects of stellar flares, regulate temperatures, and maintain the conditions necessary for liquid water. However, the intensity of Proxima Centauri's radiation poses a risk to the planet's atmosphere. If the flares are strong enough, they could gradually strip away the atmosphere, leaving Proxima-B exposed to the harsh conditions of space. For Proxima-B to retain its atmosphere and maintain habitable conditions, it would need to have a magnetic field to shield it from the radiation. Alternatively, the planet's atmosphere would need to be thick enough to resist the effects of the flares. If Proxima-B lacks both a protective magnetic field and a thick atmosphere, it may be difficult for the planet to maintain the stable conditions necessary to support life. Scientists are actively working to better understand Proxima-B's atmosphere. Using spectroscopic data from ground-based telescopes and future observations from the James Webb Space Telescope, astronomers hope to determine the composition of the planet's atmosphere and whether it contains the key gases needed for life. The presence of carbon dioxide, water vapor, and other greenhouse gases would be crucial in determining whether Proxima-B can maintain liquid water on its surface and support life. Conclusion: the possibility of life on Proxima-B. In conclusion, while Proxima-B shares many similarities with Earth, it also faces significant challenges that could limit its ability to support life. The planet's proximity to Proxima Centauri, its potential for tidal locking, and the intense stellar flaring activity from its host star all present obstacles that must be overcome. However, these challenges are not insurmountable. If Proxima-B has a strong magnetic field, a thick atmosphere, and the right geological activity, it could still provide a stable environment where liquid water exists and life could potentially thrive. The study of Proxima-B continues to be a focal point for astronomers and planetary scientists. As technology improves and new data becomes available, we may one day learn more about this intriguing exoplanet and its potential to support life. Proxima-B represents one of the closest and most promising candidates in the search for Earth-like worlds, and its study will undoubtedly shed light on the broader question of whether we are alone in the universe. Current knowledge on Proxima-B's atmosphere. As we continue our journey to understand the potential of Proxima-B to support life, we now turn our attention to the planet's atmosphere. One of the most important factors in determining whether this distant exoplanet could be habitable. The atmosphere of a planet plays a crucial role in regulating its climate, protecting its surface from harmful radiation, and maintaining the conditions necessary for liquid water to exist. Given Proxima-B's proximity to its host star, Proxima Centauri, understanding the composition and behavior of its atmosphere is a key focus for scientists trying to determine whether it could potentially support life. So far, scientists have not been able to directly observe Proxima-B's atmosphere. However, there are several ways in which astronomers can infer the composition of a planet's atmosphere without needing to land on its surface. The most common method involves using spectroscopic techniques to analyze the light from the star as it passes through the planet's atmosphere. When a planet passes in front of its star, a small amount of the star's light is filtered through the planet's atmosphere. And this can reveal information about the chemical composition of the gases present. By studying these spectral signatures, scientists can learn about the presence of gases such as carbon dioxide, water vapor, methane, and others that are essential for life as we know it. In the case of Proxima-B, the challenge of stellar flares from Proxima Centauri adds complexity to the process of studying its atmosphere. Red dwarf stars like Proxima Centauri are known for their intense flaring activity, which can emit huge amounts of radiation in the form of X-rays and ultraviolet light. These flares could potentially disrupt the planet's atmosphere, stripping away lighter gases and leaving behind only heavier elements. As a result, scientists are working to determine whether Proxima-B has a thick enough atmosphere to withstand the effects of these powerful flares, or whether the star's radiation has already stripped away much of the planet's protective gas layer. Despite these challenges, there are still some promising clues that suggest Proxima-B could have an atmosphere capable of supporting life. For one, the planet's size and mass suggest that it could have a rocky surface and the necessary gravity to retain an atmosphere. A planet's gravity plays a key role in determining whether it can hold on to an atmosphere. Too small a planet might not be able to retain its gases, while a larger planet with stronger gravity is more likely to keep its atmosphere intact. Proxima-B's gravity, which is 1.3 times that of Earth, places it in a range that could allow it to hold on to a relatively stable atmosphere over long periods of time. Another promising factor is Proxima-B's location in the habitable zone of its star. The habitable zone is the region around a star where conditions are just right for liquid water to exist on the surface of a planet. Proxima-B's position in this zone means that, in theory, the planet could have temperatures that allow for liquid water to persist, provided that its atmosphere is thick enough to regulate surface temperatures. And if Proxima-B has a substantial greenhouse effect, similar to the one that Earth experiences with carbon dioxide and water vapor, it could maintain a temperate climate and prevent water from freezing or evaporating. However, the presence of a greenhouse effect would depend heavily on the composition of Proxima-B's atmosphere. If the atmosphere is rich in carbon dioxide, methane, and water vapor, these gases could trap heat and create a stable, moderate temperature, allowing liquid water to exist on the surface. In fact, carbon dioxide and methane are some of the most important gases when it comes to regulating a planet's climate, as they are both potent greenhouse gases that can keep the planet warm enough to support liquid water. Now, the fact that Proxima-B lies in the habitable zone of its star increases the likelihood that these gases could be present in its atmosphere. But what if the atmosphere of Proxima-B is too thin or has been stripped away by stellar radiation? In this case, the planet might struggle to maintain liquid water, as it would be unable to regulate its surface temperature. A thin atmosphere would also offer little protection from the harmful radiation of Proxima Centauri's frequent stellar flares. These flares could strip away any remaining atmosphere and expose the planet's surface to dangerous radiation. Without a protective atmosphere, Proxima-B would likely become too cold on the night side and too hot on the day side, making it difficult for life to survive. Newer scientists are using observational tools like the Hubble Space Telescope and the James Webb Space Telescope to study Proxima-B's atmosphere. The James Webb Space Telescope in particular, with its ability to observe in the infrared spectrum, will allow scientists to study the composition of distant exoplanets' atmospheres in unprecedented detail. These observations will help researchers determine whether Proxima-B's atmosphere contains the gases necessary to support liquid water and, by extension, life. The ability to detect the chemical signatures of life, such as oxygen or methane, which are often associated with biological processes, could provide a breakthrough in the search for extraterrestrial life. In addition to these observational methods, scientists are also using computer simulations to model the conditions on Proxima-B. These simulations take into account the planet's distance from its star, orbital period, and assumed atmospheric composition to predict how the planet's climate might behave. The results of these models are crucial in understanding whether Proxima-B could maintain a stable atmosphere and whether its surface could support liquid water over long periods of time. While these simulations cannot provide definitive answers, they offer valuable insights into the potential for habitability on Proxima-B. One key aspect of Proxima-B's atmosphere that remains uncertain is whether it contains water vapor. Water vapor is a critical component of any planet's atmosphere, as it helps to regulate the climate and can serve as a precursor to life. The presence of water vapor could indicate that Proxima-B has active weather systems, with clouds and precipitation helping to redistribute heat and moisture across the planet. Water vapor is also a significant greenhouse gas, and its presence in the atmosphere could help to keep temperatures at a level suitable for liquid water. However, detecting water vapor in the atmosphere of an exoplanet is not a simple task. The team of scientists studying Proxima-B will need to rely on advanced spectroscopic techniques to detect the faint signatures of water vapor in the planet's atmosphere. The search for biosignatures in the atmosphere of Proxima-B is also a central focus for astronomers. If Proxima-B harbors life, it may produce gases such as oxygen, methane, or nitrous oxide, which could accumulate in the planet's atmosphere over time. These gases would be detectable through spectroscopic observations. providing scientists with the first evidence of extraterrestrial life. However, it's important to note that the presence of these gases alone is not definitive proof of life. Oxygen and methane can also be produced through non-biological processes, such as volcanic activity or chemical reactions. Still, the discovery of biosignatures would be a groundbreaking step in the search for life beyond Earth. The study of Proxima-B's atmosphere and the broader search for life beyond Earth is one of the most exciting frontiers in modern science. As technology advances and new instruments are developed, we will continue to learn more about this distant planet and its potential for supporting life. Whether or not Proxima-B harbors life, its study will help us better understand the conditions that make a planet habitable and provide important clues in the search for other Earth-like worlds. In the next part of our journey, we will explore the exciting possibilities of space missions and future exploration of Proxima-B as we continue to push the boundaries of human knowledge and discovery. The search for atmosphere signatures. As we've learned, Proxima-B sits in a unique position in the vast expanse of space. While much about this distant exoplanet remains a mystery, one of the most promising ways to unlock its secrets is through the study of its atmosphere. The composition of a planet's atmosphere is one of the most telling signs of its potential for habitability. The presence of gases such as oxygen, methane, and water vapor can indicate whether a planet has the right conditions to support life. These gases are biosignatures, potential clues that life as we know it might exist or could have existed on the planet. But how do we detect such faint traces of atmosphere and biosignatures on an exoplanet located over 4.2 light-years away from Earth? The task is not simple, but recent advancements in technology and observation methods are bringing us closer to answers. The process begins with spectroscopy, a powerful technique that allows astronomers to analyze the light emitted or absorbed by distant objects. When a planet passes in front of its star, an event known as a transit, the star's light filters through the planet's atmosphere. This light interacts with the gases in the atmosphere, and the resulting spectral signature provides crucial information about the chemical composition of the planet's atmosphere. By carefully examining these spectral fingerprints, scientists can identify which gases are present, and in some cases, even determine their quantities. For Proxima-B, this technique holds the potential to reveal vital clues about the planet's atmosphere. As Proxima-B passes in front of Proxima Centauri, its host star, astronomers can use telescopes to capture the light passing through the planet's atmosphere. This allows them to identify the molecular composition of the gases surrounding the planet. In particular, scientists are looking for the presence of oxygen, methane, carbon dioxide, and water vapor, gases that are crucial for life on Earth and are considered biosignatures. But the James Webb Space Telescope, JWST, set to launch in the near future, will be instrumental in this process. Unlike its predecessors, such as the Hubble Space Telescope, the JWST is specifically designed to observe exoplanets in much greater detail. By observing in the infrared spectrum, JWST will be able to capture more information about the composition of exoplanet atmospheres, including Proxima-B's. The JWST's sensitivity and resolution make it ideal for studying distant worlds and their atmospheres, as it can detect even the faintest spectral signatures from planets like Proxima-B. In addition to spectroscopic observations, scientists are also using computer models to simulate the atmosphere of Proxima-B. These models incorporate data from the planet's size, mass, distance from its star, and potential atmospheric composition to create a picture of what the planet's atmosphere might look like. By comparing the simulated atmospheres with the observed data from telescopes, scientists can refine their understanding of Proxima-B's environment and determine whether it has the right conditions for life. The search for biosignatures on Proxima-B is a critical step in determining whether life could exist there. If gases like oxygen or methane are detected in the planet's atmosphere, it would be an exciting indication that life might be present, or at least that the conditions for life exist. On Earth, oxygen is produced primarily by photosynthetic organisms, while methane is often produced by microbes that live in anaerobic, oxygen-free environments. If we find these gases in the atmosphere of Proxima-B, and it could suggest that the planet harbors life forms similar to those on Earth, or at least that the environmental conditions are suitable for life to thrive. However, detecting biosignatures is not a simple matter. These gases can also be produced through non-biological processes. For example, volcanic activity can release methane and carbon dioxide into the atmosphere, while chemical reactions can generate oxygen. This means that the presence of these gases alone is not definitive proof of life. Still, finding a combination of gases that cannot be easily explained by geological processes would be a strong indicator that something biological might be at work. This is why scientists are carefully analyzing the spectral data and looking for patterns that suggest the presence of life. One of the biggest challenges in studying Proxima-B's atmosphere is the planet's distance from Earth. While 4.2 light-years might not seem like a huge distance in the vastness of space, it presents significant challenges for observation. Even with advanced telescopes, such as the James Webb Space Telescope, it can be difficult to observe the faint signals from a distant exoplanet. However, recent technological advancements are improving our ability to study these far-off worlds. For example, the development of extremely sensitive spectrometers and next-generation telescopes has made it possible to detect and analyze the atmospheres of even the most distant exoplanets. As our technology improves, we may soon be able to answer the question of whether Proxima-B has an atmosphere capable of supporting life. If the planet's atmosphere contains the right gases and conditions, it could indicate that Proxima-B is one of the best candidates for finding extraterrestrial life. However, if the atmosphere is thin or lacks the necessary components, Proxima-B might be an inhospitable world with no chance for life to evolve. Even in this case, the study of Proxima-B's atmosphere will provide us with valuable insights into the conditions required for habitability and how planets in red dwarf star systems might evolve. In the near future, the James Webb Space Telescope will play a pivotal role in expanding our knowledge of Proxima-B and other exoplanets in the habitable zone. The telescope's ability to study the atmospheres of distant planets in unprecedented detail will help scientists uncover new worlds that may be similar to our own. Proxima-B, with its proximity to Earth and its potential for habitability, is an ideal target for this kind of research. As we continue to study the atmosphere of Proxima-B, we will likely learn more about the planet's potential for supporting life. The combination of advanced telescopes, computer models, and observational techniques will help us piece together the puzzle of what Proxima-B is truly like. Whether the planet harbors life or not, the answers we uncover will deepen our understanding of the conditions that make a planet habitable and move us closer to answering one of humanity's most profound questions. Are we alone in the universe? Challenges to human exploration of Proxima-B. As we venture further into the cosmos, one question persists. Can humans ever visit a distant exoplanet like Proxima-B? Proxima-B, located over 4.2 light-years away from Earth, presents both incredible opportunities and daunting challenges for space exploration. The planet's proximity to our solar system makes it an enticing target for study. But the immense distances involved, coupled with the technological limitations we currently face, make any mission to Proxima-B a formidable undertaking. First, let's consider the distance. While Proxima-B is the closest known exoplanet to Earth, it is still far beyond the reach of current human spaceflight capabilities. To put this distance into perspective, light travels about 5.88 trillion miles per year. Even at the speed of light, it would take over 4 years for a spacecraft to reach Proxima-B. However, human space exploration is not as fast as light. Current spacecraft, such as those used in missions to Mars, now travel at speeds that are only a tiny fraction of the speed of light. For example, the Parker Solar Probe, one of the fastest spacecraft ever built, travels at speeds of up to 430,000 miles per hour. At this pace, it would take over 17,000 years to reach Proxima-B, far beyond the lifespan of any human mission. This raises the fundamental challenge: how do we get there? The journey to Proxima-B would require a level of spacecraft speed and energy efficiency far beyond what we can currently achieve. To make human exploration of Proxima-B feasible, we would need to develop entirely new propulsion technologies, capable of significantly increasing the speed of spacecraft without requiring an excessive amount of fuel or energy. Several concepts have been proposed over the years, but none are currently close to being ready for operational use. One such concept is the idea of a nuclear fusion-powered spacecraft, which would harness the power of nuclear reactions to generate thrust. Fusion propulsion could theoretically provide a much higher level of efficiency and speed than traditional chemical rockets, enabling spacecraft to travel much faster and reduce travel times for long-distance missions. Fusion-powered spacecraft could potentially reach speeds of up to 10% of the speed of light, cutting the journey time to Proxima-B from 17,000 years to just 40 years. While fusion propulsion is still in the early stages of development, it holds promise for revolutionizing space travel and making interstellar exploration a reality. Another proposed method for reaching Proxima-B is the use of light sail technology. Light sails use the pressure exerted by light to propel a spacecraft forward, and they could theoretically be accelerated to speeds approaching 10% of the speed of light. The concept was demonstrated in 2016 by the Breakthrough Starshot initiative, which launched a small, lightweight spacecraft with a light sail attached, propelled by a powerful laser beam. This technology is still in its infancy, but it offers a potential way to travel to distant stars, including Proxima-B, in a matter of decades rather than centuries or millennia. However, even with the development of faster spacecraft, the long journey to Proxima-B presents other significant challenges. One of the most pressing concerns for any interstellar mission is the need to sustain human life during the journey. A journey to Proxima-B would take decades, if not centuries, and would require advanced systems for life support, food production, water recycling, and radiation protection. Prolonged exposure to the vacuum of space and the lack of gravity would have significant effects on human health, from muscle atrophy to bone density loss. Ensuring that astronauts remain healthy over the course of a multi-decade mission would require groundbreaking advancements in medical technology and life support systems. One of the most critical factors in any interstellar mission is the protection of astronauts from harmful cosmic radiation. Space is filled with high-energy particles, including cosmic rays and solar radiation, which can be damaging to human cells and DNA. Without the protection of Earth's atmosphere, astronauts on a journey to Proxima-B would be exposed to much higher levels of radiation than we experience on Earth. To mitigate this risk, spacecraft would need to be equipped with advanced radiation shielding. Possible solutions include water shielding, where water is used to absorb radiation, or magnetic shields, which would mimic Earth's magnetic field and deflect harmful particles. These technologies are still theoretical, and much more research is needed to determine how to effectively shield astronauts from the dangers of space radiation. Another challenge to human exploration of Proxima-B is the need for self-sustaining systems on the spacecraft. Unlike missions to the Moon or Mars, where supplies can be brought from Earth, a journey to Proxima-B would require a spacecraft capable of generating its own resources, including food, water, and oxygen, for decades. Astronauts would also need to be able to grow their own food and recycle their waste products to ensure a steady supply of life-sustaining resources. Closed-loop life support systems, like those being developed for long-duration missions to Mars, would need to be much more advanced to support a crew for the many years it would take to travel to Proxima-B. The journey to Proxima-B would also raise ethical questions. If a human mission were to be launched to the planet, it would likely be a one-way trip, with no possibility of returning to Earth. Would we be willing to send astronauts on a journey from which they could never come back? How would we select the crew, and what would their lives be like on such a long mission? These are questions that would need to be addressed as we consider the future of interstellar travel. Beyond the technological and ethical challenges, there are also practical considerations for any mission to Proxima-B. Funding such an ambitious endeavor would require vast resources, and it would take decades, if not centuries, to prepare. Governments and private companies alike would need to come together to invest in the development of new technologies and the establishment of a sustainable mission plan. A journey to Proxima-B would likely require international cooperation on a scale we've never seen before, as the benefits of such a mission would be felt by all of humanity. Despite the formidable challenges, the idea of sending humans to Proxima-B remains a dream for many scientists and explorers. Whilst the potential for discovering life on a planet so close to our own is one of the most exciting prospects in the field of space exploration. If we can overcome the technological, ethical, and financial hurdles, a human mission to Proxima-B could be the next great leap in the history of space exploration. In the coming years, robotic missions will likely be the first to reach the Proxima Centauri system. These missions will allow scientists to study the planet from a distance, gather data about its atmosphere and surface conditions, and determine whether Proxima-B could truly support life. While a human mission is still far off, these robotic probes will provide the groundwork for future exploration and offer valuable insights into what it might take to visit this distant world. Could humans live on Proxima-B? The idea of colonizing another planet has fascinated humanity for centuries. From the early dreams of space travel to modern discussions of settling on Mars, the desire to expand our reach beyond Earth is a powerful motivator for space exploration. Now, with the discovery of Proxima-B, the closest potentially habitable exoplanet to our own solar system, the possibility of settling on another world feels just a bit more tangible. However, while the concept of human colonization on Proxima-B is an exciting prospect, it is far from a simple or straightforward task. The first and most obvious challenge to colonization on Proxima-B is the distance. As we've discussed earlier, Proxima-B is over 4.2 light-years away from Earth. While this may seem relatively close in cosmic terms, it is still an unimaginable distance with our current space travel technology. Even with the most advanced propulsion systems available today, it would take thousands of years to reach Proxima-B. The concept of sending a human mission to Proxima-B would require breakthrough technologies, such as nuclear fusion propulsion or light sails, to accelerate spacecraft to a significant fraction of the speed of light, reducing travel times from millennia to mere decades or centuries. However, assuming we could develop such advanced technology to make the journey feasible, the next question arises: how would we survive once we arrived? Colonizing Proxima-B would require creating a self-sustaining environment capable of supporting human life. Unlike Mars, where resources like water and carbon dioxide could potentially be extracted from the planet's surface, Proxima-B offers no obvious sources of life-sustaining resources. This means that any colonization effort would have to be entirely self-reliant, relying on advanced technologies to create a livable environment for humans, creating a habitable environment. One of the first hurdles in colonizing Proxima-B would be ensuring the presence of an atmosphere capable of supporting human life. As we've discussed, Proxima-B's atmosphere is still a subject of much speculation. The planet could have a thin or unstable atmosphere due to the radiation from Proxima Centauri's frequent flares. If Proxima-B's atmosphere is stripped away, it could expose the planet's surface to the harsh conditions of space, making it inhospitable for human life. Without a thick atmosphere, Proxima-B could experience extreme temperature fluctuations, with the side facing the star becoming unbearably hot and the dark side becoming frigidly cold. In this case, humans would need to create their own atmosphere, either by using advanced terraforming techniques or by building habitat domes that can regulate pressure, temperature, and oxygen levels. Terraforming, a process by which a planet's atmosphere and surface conditions are altered to make it more Earth-like, could take centuries or even millennia to accomplish. However, scientists have speculated that small-scale terraforming could be possible by introducing greenhouse gases to warm the planet and creating conditions that could support liquid water. This would require careful planning and sophisticated technology to manage Proxima-B's delicate ecosystem. Alternatively, habitat domes or underground bases could be used to provide a controlled environment for settlers. These habitats would need to be fully self-sustaining, with advanced systems for air filtration, water recycling, and food production. The construction of such habitats would require robotic technology to build and maintain the structures, as human crews would likely be unable to undertake such large-scale construction in the early stages of colonization. Life support systems. The key to survival. For human colonization of Proxima-B to be possible, life support systems would need to be both highly reliable and long-lasting. On Earth, we take many of our life-sustaining systems for granted. Air, water, food, and shelter are all readily available. But on Proxima-B, these resources would need to be brought from Earth, grown in closed-loop systems, or recycled. Maintaining a steady supply of oxygen, food, and water for a colony of humans would be an enormous challenge, requiring the development of self-sustaining agricultural systems capable of growing food in a controlled environment. Food production could be one of the most significant obstacles. Without fertile soil and a reliable climate, colonists would have to grow their food in hydroponic or aeroponic systems, where plants are grown in nutrient-rich water or air, respectively. These systems would need to be constantly monitored and maintained to ensure the health of both the crops and the humans depending on them. In addition to food, colonists would need a steady supply of clean water, something that would likely need to be recycled or extracted from local resources, such as ice or underground water sources, if available. Radiation protection is another major concern for human settlers on Proxima-B. As we've discussed, Proxima Centauri's flaring activity could pose a significant threat to any potential colony. Without a protective magnetic field, Proxima-B's surface would be exposed to harmful radiation, which could damage both human cells and the delicate ecosystems needed to support life. To counter this, any habitats or bases on Proxima-B would need to be heavily shielded from radiation. Possible solutions include using thick water shields, building underground shelters, or using magnetic shielding to mimic Earth's protective magnetic field. And these methods would need to be tested and perfected before any long-term colonization effort could take place. Psychological and social challenges. Even if we overcome the technological hurdles, there are still significant psychological and social challenges to consider. A mission to Proxima-B would likely involve sending humans on a journey that could take decades, if not centuries. The psychological effects of such an extended mission cannot be underestimated. Long periods of isolation, limited social interaction, and confinement in a closed environment could have serious consequences for the mental health of colonists. As with missions to the International Space Station, astronauts would need to be trained to deal with the stresses of living in an enclosed space for long periods. The social dynamics of a Proxima-B colony would also need to be carefully managed. Living on a distant world would likely mean that colonists would be completely cut off from Earth. This isolation could lead to a range of issues, from loneliness and boredom to conflict among the colony's inhabitants. Maintaining morale would be essential, and providing outlets for creativity, social interaction, and recreation would be critical for long-term mental well-being. In many ways, the colony on Proxima-B would need to function as a small society, with its own systems of governance, rules, and support networks. Ethical considerations: should we colonize Proxima-B? The idea of colonizing Proxima-B also raises ethical questions. Should humanity attempt to settle on another world? Or should we focus on preserving and protecting our own planet? Some argue that the resources required for a mission to Proxima-B could be better spent addressing challenges here on Earth, such as climate change, poverty, and resource depletion. Others believe that exploring and colonizing other planets is humanity's next great frontier, providing a safety net for the survival of our species in case of a global catastrophe. Colonizing Proxima-B also raises questions about the preservation of any potential life that might exist on the planet, however microbial or primitive it may be. Planetary protection protocols, which aim to prevent contamination of other worlds, would need to be carefully considered to avoid damaging any ecosystems that might exist on Proxima-B. The future of Proxima-B exploration. While human colonization of Proxima-B is still a distant dream, the scientific exploration of this exoplanet is already underway. Robotic spacecraft, telescopes, and simulations are helping to answer critical questions about the planet's habitability. In the coming decades, missions to the Proxima Centauri system will provide new insights into this distant world and help lay the groundwork for any future human exploration. The potential for life on Proxima-B, combined with its proximity to Earth, makes it one of the most exciting targets for future exploration. Whether or not humans will one day colonize this distant planet remains uncertain. But one thing is clear: Proxima-B offers a glimpse into the future of space exploration and the possibility that we are not alone in the universe. Astrobiology and Proxima-B. One of the most exciting aspects of the discovery of Proxima-B is its potential to host life, a question that has fascinated humanity for centuries. As we look to the stars, we wonder, are we alone? Proxima-B, sitting in the habitable zone of its star, Proxima Centauri, offers a promising candidate for the search for life beyond Earth. The planet's location in the habitable zone, combined with its potential for liquid water, makes it one of the most intriguing exoplanets in the search for extraterrestrial life. But could life exist on Proxima-B? And if so, what kind of life might it harbor? And the building blocks of life. To understand the potential for life on Proxima-B, it is important to first consider what makes a planet capable of supporting life. On Earth, life is dependent on several key ingredients: liquid water, chemical elements, and a stable environment. These building blocks are essential for the formation of organic molecules, the molecules that make up all living organisms. Life, as we know it, is based on carbon, and it requires a source of energy, either from the sun or from other chemical processes, to fuel the reactions that sustain life. Given that Proxima-B lies in the habitable zone of Proxima Centauri, the conditions on the planet could allow for liquid water to exist on its surface. The presence of liquid water is one of the most crucial ingredients for life, as it serves as a solvent for chemical reactions, facilitates the movement of nutrients, and helps to regulate temperature. However, water alone is not enough. For life to thrive, the planet would also need the right chemical elements, such as carbon, nitrogen, oxygen, and phosphorus, to form the complex molecules necessary for life. The fact that Proxima-B is a rocky planet similar to Earth increases its potential for having the necessary chemical ingredients for life. Rocky planets are more likely to have the kind of solid surfaces where life could take root, compared to gas giants like Jupiter or Saturn, which lack solid surfaces. The planet's composition, which is inferred to be similar to Earth's, suggests that it could have the right mix of elements necessary for life to evolve. The role of Proxima Centauri's radiation. While Proxima-B's location in the habitable zone is promising, the conditions on the planet are far from ideal. Proxima Centauri, the star that Proxima-B orbits, is a red dwarf, a type of star that is much smaller, cooler, and more active than our Sun. Red dwarfs are known for their frequent stellar flares, intense bursts of radiation that can have a significant impact on nearby planets. These flares can release vast amounts of ultraviolet and X-ray radiation, which can be harmful to any potential life forms on Proxima-B. If Proxima-B does not have a strong magnetic field or a thick atmosphere, these flares could strip away the planet's atmosphere over time, making it more difficult for liquid water to remain on the surface. Additionally, the radiation from these flares could damage or kill any life that might exist on the planet, especially if that life is microbial. However, if Proxima-B does have a protective magnetic field, it could shield the planet from the harmful effects of these flares, allowing life to survive. A thick atmosphere could also provide some protection, filtering out harmful radiation and preventing the planet's surface from becoming too hostile for life. Another possibility is that life on Proxima-B could thrive beneath the surface, shielded from the radiation of Proxima Centauri. Much like the subsurface oceans found on moons like Europa and Enceladus, Proxima-B could have a layer of water beneath its surface, kept warm by geothermal heat or tidal forces from its orbit around Proxima Centauri. These subsurface environments could provide a stable, protected environment where microbial life could survive, even in the face of intense stellar radiation. Searching for signs of life on Proxima-B. The search for life on Proxima-B will involve a combination of observational techniques and computer simulations. To begin with, scientists will use spectroscopy to study the planet's atmosphere for signs of potential biosignatures. Spectroscopic data from telescopes, like the James Webb Space Telescope and the Hubble Space Telescope, will allow astronomers to detect the presence of key gases like oxygen, methane, and carbon dioxide, which could be produced by biological processes. The detection of these gases, particularly in combination, could suggest that Proxima-B harbors life. However, the presence of these gases alone is not definitive proof of life. These gases can also be produced through geological processes, such as volcanic activity, or by chemical reactions in the planet's atmosphere. This is why astronomers are also looking for patterns in the spectral data that might indicate biological activity. For example, the presence of oxygen and methane in large quantities, in combination with other gases like nitrogen, could indicate that biological processes are at work. On Earth, these gases are produced by living organisms, particularly photosynthetic organisms that release oxygen and methanogens that produce methane in oxygen-free environments. In addition to spectroscopic observations, scientists are using computer models to simulate the conditions on Proxima-B and determine whether the planet could support life. These models take into account the planet's distance from its star, its orbital period, size, and potential atmospheric composition to predict whether conditions on the planet might be suitable for life. The results of these simulations will help guide future observations and determine whether Proxima-B is truly a habitable world. The search for life beyond Earth. Proxima-B is just one of many exoplanets in the habitable zone of their stars, and its discovery has opened up exciting possibilities for the search for extraterrestrial life. While the conditions on Proxima-B may be harsh, the planet's proximity to Earth makes it an ideal target for further study. By learning more about Proxima-B and its potential for hosting life, scientists can improve our understanding of what makes a planet habitable and increase the likelihood of discovering life elsewhere in the universe. The search for life beyond Earth is one of the most profound quests in science, and Proxima-B is one of the most promising places to search for answers. Whether life exists on Proxima-B or not, the study of this distant world will provide valuable insights into the conditions required for life and bring us closer to answering the age-old question: are we alone in the universe? The future of astrobiology and Proxima-B. As we look to the future, the study of Proxima-B and other exoplanets will continue to be a key focus for astrobiologists and planetary scientists. New technologies, like the James Webb Space Telescope and future space missions, will provide unprecedented detail about the atmospheres of distant planets. These advancements in technology will allow us to detect biosignatures, search for signs of life, and understand the conditions required for life to exist beyond Earth. The future of astrobiology is bright, and Proxima-B is at the forefront of this exciting field. Whether or not we find life on this distant planet, the search will push the boundaries of our knowledge and expand our understanding of the universe. Proxima-B represents a stepping stone in the search for life, a reminder that life could exist beyond Earth, waiting to be discovered by future generations of explorers. Despite these differences, Proxima-B's overall characteristics, its size, gravity, location in the habitable zone, and potential for water, make it one of the most exciting exoplanets discovered to date. As we continue to study Proxima-B and gather more data, scientists will work to refine our understanding of this distant world and its potential for supporting life. Future observations with advanced telescopes, such as the James Webb Space Telescope, will provide new insights into the planet's atmosphere, surface conditions, and whether it might one day harbor microbial life. Searching for signals, SETI and Proxima-B. As we continue our exploration of Proxima-B, we turn our attention to one of the most exciting aspects of the search for life beyond Earth: the possibility of detecting extraterrestrial signals. While the presence of liquid water, the right chemicals, and an Earth-like atmosphere all point toward the potential for life on Proxima-B, the next step in our quest for knowledge is to listen for signs that intelligent life might exist there. This brings us to the work of SETI, the search for extraterrestrial intelligence. For decades, scientists have been scanning the skies for signals from distant stars, hoping to detect evidence of alien civilizations. The idea is simple. If an intelligent species exists on a distant planet like Proxima-B, they may have developed technology capable of sending signals into space. By listening for these signals, we might one day make contact with beings from another world. This search is often referred to as the SETI program, and it has been one of the cornerstones of astrobiology and the search for extraterrestrial life. Proxima-B, being one of the closest potentially habitable planets to Earth, is a prime target for SETI. The proximity of Proxima-B makes it an ideal candidate for detecting radio signals or other forms of electromagnetic communication. And these signals could be coming from an advanced civilization on Proxima-B, or they could be evidence of technological activity, like the emission of laser beams or other forms of interstellar communication. While the chances of finding intelligent life on Proxima-B are still speculative, the potential for discovery makes it a compelling target for SETI. The search for extraterrestrial signals is based on the assumption that advanced civilizations might use technology similar to our own. Just as we use radio waves and microwaves to communicate over long distances, it's possible that an alien civilization on Proxima-B could be using similar methods to send information across the stars. The radio waves we use to communicate with spacecraft like Voyager 1 and Parker's solar probe are some of the most likely candidates for detecting extraterrestrial signals. These waves travel through space at the speed of light and can travel vast distances without losing much energy. If an alien civilization on Proxima-B were to emit a radio signal, it could potentially be detected by radio telescopes on Earth. One of the most famous SETI projects is the search for narrowband radio signals. These are signals that have a very specific frequency, unlike the random noise that typically fills space. Narrowband signals are often associated with radio transmitters and could indicate the presence of a technological civilization. SETI scientists are constantly on the lookout for these kinds of signals, and they have been scanning the skies for decades in hopes of making contact with intelligent life. While the search for narrowband radio signals is one of the main focuses of SETI, researchers are also exploring other possibilities for detecting extraterrestrial communication. One such method is the search for laser pulses, which could be used by an advanced civilization to communicate over long distances. Laser beams are incredibly precise and can travel vast distances with little loss of energy. If an intelligent civilization on Proxima-B were to emit a laser signal, it could potentially be detected by ground-based telescopes or even space telescopes. In recent years, the discovery of fast radio bursts, FRBs, highly energetic pulses of radio waves, has sparked interest in the possibility that these bursts could be artificial in origin. Brilliant FRBs have been detected coming from deep space, and while their exact cause is still unknown, some scientists speculate that they could be the result of extraterrestrial technology. Despite the excitement surrounding the search for extraterrestrial signals, it's important to acknowledge the challenges of this pursuit. Proxima-B, while relatively close to Earth, is still over 4 light-years away, and any signals we receive from it would take years to reach us. Moreover, the technology required to send and detect interstellar signals is still in its early stages. While we have made significant strides in the development of radio telescopes and other observational tools, the vast distances involved in interstellar communication present significant hurdles. The signals we might detect from Proxima-B could be weak and difficult to distinguish from the natural noise of the cosmos. Additionally, any potential civilization on Proxima-B might not be using the same methods of communication that we are familiar with, which could make it even harder to detect their signals. One of the most famous instances of a SETI search involved the detection of the WOW signal in 1977. This narrowband radio signal, detected by the Big Ear radio telescope at Ohio State University, was never fully explained. It remains one of the most intriguing mysteries in the search for extraterrestrial intelligence. Although scientists have not been able to determine the source of the WOW signal, it serves as a reminder of how difficult and elusive the search for extraterrestrial signals can be. Proxima-B, and with its proximity and potential for life, could very well be the next target for similar investigations. In recent years, there has been renewed interest in SETI research, particularly with the advent of more advanced telescopes and new technologies. The Breakthrough Listen initiative, a global project launched in 2015, is one of the most ambitious SETI efforts to date. This project aims to scan the entire sky for radio signals and laser pulses, and it is using some of the world's most powerful radio telescopes to do so. With the help of cutting-edge technology, we are now in a better position than ever to search for signals from Proxima-B and other exoplanets. The James Webb Space Telescope, set to launch in the near future, will be another valuable tool in the search for extraterrestrial signals, while its primary mission is to study the atmospheres of exoplanets and look for signs of habitability. It may also be able to detect technosignatures, evidence of artificial technology. The James Webb Space Telescope will provide unprecedented views of distant planets, including Proxima-B, and will help astronomers identify signs of life, whether biological or technological. The search for signals from Proxima-B is not just about finding extraterrestrial life. It's about understanding our place in the universe. If we were to receive a signal from an alien civilization, it would be one of the most profound discoveries in human history. It would tell us that we are not alone and that life is more common in the universe than we ever imagined. Even if we do not find a signal from Proxima-B, the search itself is invaluable. It drives advancements in technology, expands our understanding of the universe, and reminds us of the vast possibilities that lie beyond our planet. In the future, as we continue to develop new technologies and deepen our understanding of the universe, the search for signals from planets like Proxima-B will remain a central focus of SETI. The prospect of discovering extraterrestrial life, whether through signals or other means, is an ongoing pursuit that holds the promise of answering one of humanity's most profound questions. Are we alone? Upcoming space missions to Proxima-B. As we continue to look toward the stars, the exploration of Proxima-B is poised to play a pivotal role in the future of space exploration. With its potential to host life, proximity to Earth, and intriguing similarities to our own planet, Proxima-B is an exciting target for future space missions. Although a human mission to Proxima-B is still far in the future, robotic spacecraft and cutting-edge telescopes are already being developed to gather invaluable data about the planet. These upcoming missions will provide new insights into the atmosphere, surface conditions, and habitability of this distant exoplanet, bringing us one step closer to answering the question, can Proxima-B support life? One of the most exciting missions in the study of Proxima-B is the James Webb Space Telescope, JWST. Set to launch in the near future, the JWST is one of the most advanced observatories ever built. It is designed to observe the universe in the infrared spectrum, which allows it to study distant exoplanets and their atmospheres in unprecedented detail. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet spectra, the JWST's infrared capabilities will enable it to detect faint heat signatures from exoplanets, even those as distant as Proxima-B. The JWST will be able to directly study Proxima-B's atmosphere, looking for key biosignatures such as water vapor, methane, carbon dioxide, and oxygen. These gases are essential components of a planet's ability to support life, and their detection would provide compelling evidence that Proxima-B could potentially host life. In addition to searching for biosignatures, the JWST will also be able to study the planet's climate, weather patterns, and geological activity, shedding light on the potential habitability of this distant world. By analyzing the spectral data from Proxima-B's atmosphere, the JWST will help scientists understand the composition of the planet's air and the conditions necessary for liquid water to exist on its surface. While the James Webb Space Telescope will provide invaluable data from a distance, robotic missions to the Proxima Centauri system could offer more detailed, hands-on exploration of Proxima-B. Although no mission to Proxima B is currently planned, several ambitious proposals are being considered by the scientific community. One of the most exciting ideas is the concept of a flyby mission to Proxima B. A flyby mission would involve sending a spacecraft to pass close to Proxima B, allowing it to gather data on the planet's atmosphere, magnetic field, radiation levels, and other key factors that determine its habitability. While a flyby mission would not involve landing on the planet, it could still provide crucial insights into Proxima B's potential for supporting life. One of the most promising proposals for a Proxima B flyby mission is the Breakthrough Starshot Initiative, a project aimed at sending small, lightweight spacecraft to the nearest star systems, including Proxima Centauri. The goal of Breakthrough Starshot is to develop a fleet of starships, tiny, solar-powered spacecraft that would be capable of traveling at a significant fraction of the speed of light. These spacecraft would be propelled by powerful laser beams and could reach Proxima Centauri in as little as 20 years. Once there, the starships would send back data about Proxima B, including information on its atmosphere, surface conditions, and potential for life. Although Breakthrough Starshot is still in the early stages of development, its ambitious goals represent a bold step forward in the quest to explore the stars. In addition to Breakthrough Starshot, several other space agencies are exploring the possibility of sending robotic missions to study Proxima B and other exoplanets in detail. The European Space Agency, ESA, for example, is planning to launch the Ariel mission in the near future. Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, will study the atmospheres of a large sample of exoplanets, including those in the habitable zone of their stars. While Ariel is not specifically focused on Proxima B, it will contribute to the broader understanding of exoplanet atmospheres and help inform future missions to planets like Proxima B. Another potential mission to consider is the NASA Habitable Exoplanet Imaging Mission, HabEx, which is currently in the concept phase. HabEx aims to directly image and study the atmospheres of Earth-like exoplanets, looking for signs of habitability and potential biosignatures. HabEx would use starshade technology to block out the light from distant stars, allowing it to observe faint exoplanets like Proxima B in greater detail. By studying the spectra of these planets, HabEx could detect the presence of key gases associated with life and provide more information about their potential for supporting life. In the future, lander missions could become a possibility. While landing on Proxima B would be an enormous challenge given the planet's distance, future advancements in propulsion and life support systems could make such a mission possible. A Proxima B lander would be able to study the planet's surface directly, examining the soil, atmosphere, and radiation levels in great detail. Such a mission would provide a wealth of information about the planet's ability to support life. But it is still many years away from becoming a reality. Beyond studying Proxima B itself, future space missions could also explore the broader Proxima Centauri system. The discovery of other planets around Proxima Centauri, especially those in the habitable zone, could lead to exciting new missions. For example, researchers are particularly interested in the possibility of moons orbiting Proxima B, as moons in the habitable zone could provide additional opportunities for life. These moons could potentially have stable environments, with liquid water on their surfaces and atmospheres capable of sustaining life. A mission to study the moons of Proxima B would add another layer of excitement to the exploration of the Proxima Centauri system. While all of these missions are still in the planning stages, they represent the future of space exploration and interstellar discovery. The tools and technologies being developed for these missions are advancing rapidly, and in the coming decades, we may see the first missions to study Proxima B and other exoplanets in unprecedented detail. These missions will not only help us understand Proxima-B's potential for supporting life, but also pave the way for future missions to other distant worlds. Conclusion: the future of exploration. The future of space exploration is undoubtedly exciting, and Proxima-B is at the forefront of this new frontier. Whether it's through telescopic observations, robotic missions, or future human exploration, Proxima-B will continue to capture the imagination of scientists and explorers alike. The insights we gain from studying Proxima-B will deepen our understanding of the conditions required for life and help guide our search for other habitable planets in the universe. As technology continues to advance, the dream of visiting Proxima-B and other distant exoplanets may become a reality. The upcoming space missions will provide us with the tools to unlock the secrets of this distant world, bringing us one step closer to answering one of humanity's most profound questions. Are we alone in the universe? Broader implications for space exploration and humanity. The discovery of Proxima-B is not just a scientific milestone. It's a philosophical and cultural turning point for humanity. As one of the most Earth-like planets discovered so far, Proxima-B represents more than just another exoplanet in a distant star system. It represents the possibility that we are not alone in the universe, and that life, as we know it, or perhaps in forms we have yet to imagine, could be more common than we ever thought. This realization brings with it profound implications for both the future of space exploration and our understanding of life in the cosmos, reinforcing the search for life beyond Earth. For centuries, humans have wondered whether life exists elsewhere in the universe. From early mythologies and philosophical speculations to modern scientific endeavors, the search for extraterrestrial life has been a driving force in the history of human thought. The discovery of Proxima-B, a planet potentially capable of sustaining life, brings that long-standing question one step closer to an answer. But the implications of this discovery go beyond just Proxima-B itself. They open up new avenues for astrobiology and the search for life on other exoplanets. Proxima-B is a golden opportunity for scientists to study the conditions that could support life on planets outside our solar system. With its proximity to Earth, just 4.2 light-years away, Proxima-B is a prime target for future observations and missions. It's a reminder that life, at least in some form, may be common in the universe, and that the search for life is not confined to the boundaries of Earth. The fact that Proxima-B is so close also underscores the importance of developing the technologies needed to study exoplanets in greater detail. We are on the cusp of an era in which interstellar exploration might become possible, and Proxima-B is a natural starting point. The James Webb Space Telescope, as well as future space missions, will provide us with the tools to understand the potential for life on planets in distant star systems. If Proxima-B holds clues to the origin of life or the possibility of other forms of existence, it could radically change how we view the universe and our place in it. A new perspective on our own Earth. As we study Proxima-B and other exoplanets, we are also forced to take a closer look at our own planet, Earth. Proxima-B's discovery provides a mirror through which we can better understand the delicate balance that allows life to thrive on our own world. While Earth has abundant resources, a stable climate, geophysics, and a magnetic field that protects us from the harmful effects of cosmic radiation, Proxima-B's challenges highlight how fragile these conditions are. If Proxima-B does indeed have liquid water and conditions that could support life, it will be a profound reminder of how rare and precious our Earth is. The planet's potential for habitability underscores the necessity of preserving our environment and ensuring the long-term survival of our species. Our quest to explore other planets and search for life beyond Earth is not just about seeking new frontiers. It is also about preserving our home and understanding the delicate ecological systems that sustain us. The discovery of Proxima-B serves as a wake-up call. If we are to protect the Earth from the increasing challenges of climate change, resource depletion, and environmental destruction, we need to learn as much as possible from planets like Proxima-B. By studying exoplanets, scientists can gain insights into the forces that shape planets and ecosystems, helping us to better understand how our own planet functions and how we can protect it from irreversible harm. Philosophical implications. Are we alone? The search for life on Proxima-B and other exoplanets also raises profound philosophical questions about our place in the universe. If we find evidence of life beyond Earth, it would challenge many of the assumptions we've held about our uniqueness as a species. For centuries, humanity has viewed itself as the pinnacle of evolution on Earth, with no known equals in the vast expanse of space. But the discovery of life, especially intelligent life, on another planet would shake this belief to its core. If life exists elsewhere, it raises the question of whether we are truly alone in the universe. Are there civilizations out there, intelligent and technologically advanced, capable of communicating across the stars? Or is life on other planets still in its most primitive forms, much like early Earth? If Proxima-B harbors microbial life, this would suggest that life can emerge in many different environments across the universe, making the cosmos seem much more alive than we ever imagined. Cultural and societal impact. The discovery of life on Proxima-B, or the possibility of future human colonization of the planet, would have profound effects on culture and society. Science fiction has long explored the theme of life beyond Earth. From stories of first contact with alien civilizations to tales of interstellar travel and colonization, these stories have captured the human imagination and shaped our vision of the future. Now, as we venture closer to the possibility of actually discovering life beyond Earth, those once imagined scenarios might begin to take on a more tangible form. The idea of life on Proxima-B could inspire new cultural narratives and influence the arts, philosophy, and even politics. As the search for extraterrestrial life becomes more real, it will shape how we view our own place in the universe. Will we see ourselves as part of a greater cosmic community? Or will we remain focused on our terrestrial concerns? How will we respond if we find life, or even intelligent civilizations, on distant planets? The exploration of Proxima-B may also encourage future generations to take an active role in the pursuit of space exploration and interstellar communication. As we learn more about exoplanets and their potential for habitability, we may see an increase in the global collaboration needed to achieve space exploration goals. The desire to learn more about distant worlds could lead to greater investments in space programs, both governmental and private, and could inspire future generations to study astrobiology, astronomy, engineering, and other fields that are essential to space exploration. The future of Proxima-B and interstellar exploration. Looking forward, the future of Proxima-B and interstellar exploration holds immense potential. As we develop new technologies for faster spacecraft and longer-lasting life support systems, the dream of sending humans to distant exoplanets like Proxima-B could become a reality. With continued advances in propulsion systems, radiation protection, and self-sustaining ecosystems, interstellar travel may become possible within the next century. In the near term, robotic missions will continue to explore Proxima-B and other exoplanets, using powerful telescopes and space probes to gather data and answer critical questions about the potential for life. The data collected will lay the groundwork for future human missions and provide insights into how we might survive and thrive on distant worlds. As we look to the future, the exploration of Proxima-B and other exoplanets will continue to be a symbol of humanity's curiosity, ambition, and search for knowledge. The challenges are immense, but the potential rewards, discovery on new frontiers, and perhaps even the confirmation of life beyond Earth, are worth the effort. In the next section, we will look at interstellar travel technologies, exploring how far we have come and what remains to be done in order to make missions to planets like Proxima-B a reality. The future is full of possibilities, and Proxima-B may be the key to unlocking the secrets of life beyond Earth. Interstellar travel technologies. As we explore the possibilities of reaching distant exoplanets like Proxima-B, we must consider the most fundamental question of all. How can we travel to stars that are so far away? The distance to Proxima-B, about 4.2 light-years, makes it one of the closest potentially habitable exoplanets to Earth. Yet, it is still a staggering distance for any current spacecraft. Even with our most advanced propulsion systems, a journey to Proxima-B would take thousands of years. However, scientists and engineers are not deterred by the vast distances. They are already developing new technologies that could make interstellar travel a reality within the next few centuries. These technologies could pave the way for missions to Proxima-B and other distant exoplanets, expanding humanity's reach beyond our solar system. Current space propulsion technologies. At present, space travel is limited by the capabilities of traditional propulsion systems. The most commonly used propulsion systems for interplanetary missions are chemical rockets, which use the energy released from chemical reactions to propel spacecraft. While chemical rockets are highly effective for launching spacecraft from Earth and reaching nearby planets, they are not suitable for interstellar travel. The speeds achievable by chemical rockets are much too slow to reach distant stars in any reasonable time frame. For example, the fastest spacecraft ever built, NASA's Parker Solar Probe, travels at a speed of about 430,000 miles per hour. At that speed, it would take over 17,000 years to reach Proxima-B. To overcome these limitations, scientists are researching alternative propulsion technologies that could accelerate spacecraft to much higher speeds. Among the most promising options are nuclear propulsion, solar sails, and ion drives, each of which offers a potential path forward for interstellar exploration. Nuclear propulsion, a quantum leap. One of the most promising technologies for interstellar travel is nuclear propulsion. A nuclear-powered spacecraft could use the immense energy released by nuclear fission or fusion to propel spacecraft to much higher speeds than chemical rockets can achieve. There are two primary approaches to nuclear propulsion: nuclear fission and nuclear fusion. Nuclear fission propulsion works by using the energy from nuclear reactions to heat a propellant, which is then expelled through a nozzle to generate thrust. The advantage of fission propulsion is that it could provide much higher levels of efficiency and thrust compared to chemical rockets. While this technology is still in the early stages of development, it could eventually allow spacecraft to travel to the outer planets and beyond, reducing travel times to distant stars like Proxima-B to decades instead of millennia. Even more promising is nuclear fusion propulsion, which harnesses the energy produced by fusing atomic nuclei, much like the process that powers the sun. Fusion propulsion could offer an even greater leap in efficiency, potentially allowing spacecraft to reach 10% of the speed of light. At this speed, a journey to Proxima-B could take as little as 40 years. However, nuclear fusion is still a theoretical technology, and scientists have yet to develop a viable fusion reactor that can provide the necessary power for propulsion. Despite this, research is progressing, and if nuclear fusion propulsion becomes a reality, it could revolutionize space travel, making interstellar missions possible within our lifetimes. Solar sails. Harnessing the power of light. Another exciting concept for interstellar travel is solar sails. Solar sails use light pressure, the force exerted by photons of light, to propel spacecraft across space. This technology is based on the principle that light, even though it has no mass, exerts a small amount of pressure when it strikes an object. By capturing this light pressure, a spacecraft can be propelled forward, gradually building up speed over time. Solar sails have the potential to achieve incredibly high speeds, with some designs speculating they could eventually reach speeds of up to 10% of the speed of light. The primary advantage of solar sails is that they don't require fuel. They rely solely on the power of sunlight or laser beams to provide thrust. A spacecraft with a solar sail could be launched from Earth and gradually accelerate toward its destination, relying on the continuous force of light to propel it through space. Solar sails have already been tested in small-scale missions, such as the Icaros mission by the Japan Aerospace Exploration Agency, JAXA, and Breakthrough Starshot, an ambitious project aimed at sending small probes to nearby star systems, including Proxima Centauri. The Breakthrough Starshot initiative is one of the most ambitious attempts to use solar sails for interstellar travel. The project plans to send tiny, lightweight spacecraft, known as starships, to Proxima Centauri, using powerful laser beams to propel them to speeds of 20% of the speed of light. If successful, these spacecraft could reach Proxima-B in just 20 years. While the technology is still in its infancy, the potential for solar sails to revolutionize interstellar travel is immense. The ion drives, efficient and long-lasting. Another propulsion technology that shows promise for interstellar missions is ion propulsion. Ion drives work by ionizing a gas, usually xenon, and using electric fields to accelerate the ions to extremely high speeds, creating thrust. While ion propulsion systems provide much lower thrust than chemical rockets, they are incredibly efficient and can operate for long periods, making them ideal for long-duration missions. The NASA Dawn spacecraft, which visited the dwarf planet Ceres, used ion propulsion for its journey through the asteroid belt, demonstrating the viability of this technology for deep space exploration. Ion drives could be used for interstellar missions, though they would still require many years to reach even nearby stars. The advantage of ion propulsion is its efficiency. It uses a fraction of the fuel required by traditional chemical rockets, allowing spacecraft to travel for extended periods with minimal fuel. For missions to Proxima-B or other distant exoplanets, ion drives could be paired with other technologies, such as nuclear fusion or solar sails, to accelerate spacecraft to higher speeds. Challenges to interstellar travel. While the potential for interstellar travel is exciting, it is important to acknowledge the many challenges that remain. The vast distances between stars are the primary obstacle to interstellar exploration. Even with advanced propulsion technologies, the journey to Proxima-B would take decades or centuries, presenting significant challenges for human explorers, including the need for life support systems, radiation protection, and sustainable resources. Another challenge is the dangerous environment of interstellar space. Space is filled with high-energy particles and cosmic radiation that could damage spacecraft and harm astronauts. To protect against these dangers, spacecraft would need to be equipped with advanced shielding and radiation protection technologies. Developing these systems is essential to ensuring the safety of future interstellar missions. Finally, the long duration of interstellar travel presents social, psychological, and ethical challenges. How would humans cope with isolation, confinement, and the immense timescales required for such missions? Who would undertake such journeys, and what would life be like on board these distant spacecraft? These questions are as important as the technical challenges and must be considered carefully as humanity looks toward interstellar exploration. The future of interstellar exploration. Despite these challenges, the future of interstellar exploration holds tremendous potential. The development of new propulsion systems, advanced life support technologies, and spacecraft protection systems will pave the way for missions to distant exoplanets like Proxima-B. While such missions are still decades or centuries away, the progress being made in propulsion technology, coupled with the growing interest in space exploration, suggests that interstellar travel could one day be within our reach. As we develop the technologies needed to explore distant stars, we will continue to learn more about the nature of the universe and the potential for life on other worlds. Proxima-B, with its proximity to Earth and potential for habitability, serves as a beacon for the future of space exploration. A reminder that we are not just Earthbound, but part of a much larger cosmos. The role of international collaboration in space exploration. As we venture deeper into the realm of interstellar exploration, the complexity and scope of these missions demand a level of global cooperation that goes beyond national boundaries. While individual countries have long led the charge in space exploration, the challenges of reaching distant exoplanets like Proxima-B require pooling resources, expertise, and funding from across the globe. Interstellar missions, not just about sending spacecraft to the stars. They are about creating a shared vision for the future of humanity, one that transcends national interests and focuses on collective discovery. The journey to Proxima-B, with its staggering distance and the need for advanced propulsion systems, life support technologies, and radiation protection, is too enormous a task for any single country to undertake alone. The collaboration between space agencies, universities, private companies, and governments will be essential to ensure that humanity can successfully explore the stars. But how can international cooperation help us overcome the challenges of interstellar exploration? And what role do global partnerships play in the success of missions to distant worlds? Space agencies working together. A unified effort. One of the most prominent examples of international collaboration in space exploration is the International Space Station, ISS, a partnership between the United States, NASA, Russia, Roscosmos, Europe, ESA, Japan JAXA, and Canada, CSA. The ISS has provided valuable experience in building and operating a permanent space station, bringing together the best minds and technologies from around the world. Over 2 decades of collaboration have shown that when countries put aside differences and focus on common goals, great achievements are possible. The ISS has not only fostered collaboration between countries, but has also served as a testbed for technologies that will be crucial for future missions, especially those beyond the Moon and Mars. Life support systems, radiation shielding, REHAR, and long-duration human health in space have been tested aboard the ISS, providing data that will be critical for interstellar missions. These technologies, along with robotic exploration systems and planetary landing techniques, will be crucial as humanity looks to travel further into the cosmos. Similarly, space telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope represent a collaborative effort between space agencies around the world. NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA, have all contributed to these missions, which are designed to explore the universe and provide detailed data on distant exoplanets like Proxima-B. Without the combined expertise and funding from multiple countries, these missions would be far less feasible. The James Webb Space Telescope, set to launch soon, will allow us to study the atmospheres of exoplanets, detect signs of life, and gather crucial data that will help us determine the habitability of distant worlds. As we look beyond our solar system, space agencies like NASA, the European Space Agency, ESA, China's Space Agency, CNSA, and India's Space Agency, ISRO, are all making significant strides in the search for exoplanets. These agencies are working together through initiatives like the Exoplanet Exploration Program, where they share data, observations, and mission results in the pursuit of discovering potentially habitable worlds. The combined expertise of these organizations makes it possible to tackle the enormous challenge of interstellar exploration and ensures that no single country is left behind in the quest to understand our place in the universe. So private companies, pioneers of new technologies. In addition to governmental space agencies, the involvement of private companies in space exploration is playing an increasingly important role in the development of interstellar missions. Companies like SpaceX, Blue Origin, and Boeing are pushing the boundaries of space technology with new innovations in reusable rockets, spacecraft design, and propulsion systems. These companies are not only making space more accessible, but are also contributing to the development of the technologies that will be necessary for interstellar travel. SpaceX, for example, has made significant advancements in rocket reusability with its Falcon 9 and Starship programs. These developments have dramatically reduced the cost of space launches, making it more feasible to send payloads to distant destinations, including potential missions to Proxima-B. The Starship program, in particular, aims to create a fully reusable spacecraft capable of carrying humans to destinations like Mars, the Moon, and potentially beyond. This reusability will be essential for future interstellar missions, as it will make long-term space travel more economical and sustainable. Private companies are also leading the charge in propulsion innovation, with companies like Blue Origin developing new rocket engines and space propulsion systems that could one day be adapted for interstellar travel. By focusing on efficient propulsion technologies, these companies are helping to lay the groundwork for the faster spacecraft that will be necessary for reaching distant exoplanets like Proxima-B. These advancements are essential for reducing travel time and making interstellar missions a reality. The Breakthrough Starshot initiative, which we mentioned earlier, is a prime example of a public-private partnership aimed at sending small probes to Proxima Centauri and other star systems. The project, spearheaded by Breakthrough Initiatives, is a collaboration between scientists, engineers, and private sector funding to develop light sail technology. This technology could enable spacecraft to travel at a significant fraction of the speed of light, making the journey to Proxima-B possible in a matter of decades. Breakthrough Starshot is a clear example of how private sector innovation and governmental cooperation can work together to push the boundaries of space exploration. To international collaboration, the key to success. When it comes to interstellar exploration, no single country or organization can accomplish the task alone. The challenges of sending a spacecraft to Proxima-B, funding the mission, and developing the necessary technologies are simply too great for any one nation to handle. The future of space exploration will depend on the ability of countries, space agencies, and private companies to work together toward common goals. By sharing resources, data, and expertise, international collaborators can tackle the enormous challenges of interstellar travel more effectively. Whether it's sharing the cost of spacecraft development, collaborating on propulsion research, or working together to design long-term human habitats for interstellar missions. The success of future missions to Proxima-B and other distant worlds will depend on global cooperation. In addition to technical cooperation, international collaboration also fosters a sense of shared humanity in the pursuit of knowledge and exploration. As we look beyond our solar system, it is important to remember that space exploration is a global endeavor. It transcends borders, unites nations, and reminds us that we are all part of the same planet and the same cosmos. The search for life on Proxima-B and the dream of interstellar travel are not just scientific goals. They are shared aspirations that speak to the deepest parts of our collective imagination. Looking ahead, a unified vision for the future. Looking ahead, the future of interstellar exploration will rely on the continued collaboration of space agencies, our private companies, and international partners. The development of faster propulsion systems, radiation shielding, and sustainable life support technologies will require a concerted effort from all sectors of society. As we continue to develop new technologies, the dream of reaching Proxima-B and other distant exoplanets will gradually become more achievable. The study of Proxima-B and other exoplanets will provide humanity with crucial insights into the potential for life beyond Earth. It will help us understand what makes a planet habitable, how life might thrive on distant worlds, and how we might one day travel to these stars ourselves. The journey is long and challenging, but the potential rewards, discovery, knowledge, and perhaps the confirmation of extraterrestrial life are worth the effort. In the coming decades, we will see a shift toward interstellar missions, and Proxima-B will remain one of the most important targets for exploration. Through continued global collaboration, innovation, and investment, humanity will one day set foot on distant worlds, unlocking the mysteries of the universe and answering the age-old question, are we alone? Philosophical and cultural implications of exploring Proxima-B. The quest to explore Proxima-B and other distant exoplanets is not only a scientific pursuit. It is a deeply philosophical endeavor that raises profound questions about our place in the universe and the nature of life itself. As we send spacecraft to study Proxima-B, the closest potentially habitable exoplanet, we are forced to confront some of the most fundamental and existential questions that humanity has grappled with for centuries. And these questions go beyond the realms of physics and biology. They touch on our collective identity, our purpose, and our future as a species. The study of Proxima-B and the search for life beyond Earth have the potential to redefine our understanding of life and the universe. As we look to the stars, we are not just seeking other worlds. We are searching for answers to the age-old question, are we alone? Finding evidence of life on Proxima-B or another exoplanet would be one of the most transformative discoveries in human history, fundamentally altering how we see ourselves in relation to the cosmos. The search for meaning. What does it mean to find life beyond Earth? The discovery of life beyond Earth would force us to reconsider some of our most deeply held beliefs about life and intelligence. On Earth, we have long believed that our planet is unique, that life, particularly intelligent life, is a product of a rare set of conditions. If we were to find evidence of microbial life on Proxima-B or another distant exoplanet, it would suggest that life is not a one-time event, but rather a process that could occur elsewhere in the universe under the right conditions. This realization would challenge our perceptions of Earth's specialness and open the door to the possibility that life is widespread throughout the cosmos. The implications would be vast. If life can thrive on a planet like Proxima-B, it would suggest that the universe is far more alive than we ever imagined. Perhaps life exists on countless planets, each with its own unique forms, from microbes to intelligent civilizations. This would shift our perspective from being the sole stewards of life in the universe to being part of a larger cosmic community. It could bring about a philosophical shift, one that moves humanity away from its self-centered view of the cosmos to a more humble and connected understanding of our place in the universe. But the question remains, what would it mean to truly discover life beyond Earth? The discovery could alter human culture, challenging our religious beliefs, our societal norms, and our assumptions about the nature of life itself. It could prompt a paradigm shift in human thinking, just as the discovery of the heliocentric model of the solar system challenged the beliefs of the time. For many, discovering life beyond Earth could be seen as proof that we are part of something much larger than ourselves. A revelation that could inspire unity and hope for the future. Proxima-B and the concept of the Great Filter. The discovery of Proxima-B and other exoplanets in the habitable zone of their stars also forces us to confront the Fermi paradox and the concept of the Great Filter. The Fermi paradox asks the question, if the universe is so vast and filled with potentially habitable planets, why haven't we found any signs of intelligent extraterrestrial civilizations? Some scientists propose that there may be a filter, a barrier that prevents civilizations from surviving long enough to make contact or travel to the stars. The Great Filter could exist at any stage of a civilization's development, from the emergence of life to the development of advanced technology capable of interstellar travel. If life exists on Proxima-B, it could provide clues about the Great Filter, whether it is something that life on Earth has already passed or whether we are yet to face it. If we discover that life has emerged on Proxima-B, it could suggest that the Great Filter is not related to the emergence of life itself, but rather to the development of intelligent civilizations capable of interstellar communication. This would raise difficult questions about whether humanity is truly destined to become an interstellar species, or whether we are just one of many civilizations that ultimately fail to reach the stars. On the other hand, if we find that Proxima-B does not harbor life, it could suggest that the Great Filter is tied to the emergence of life, and that Earth's biosphere is a rare anomaly in the universe. This would give new urgency to the preservation of life on Earth, as we may be one of the few planets capable of sustaining life in the cosmos. The role of space exploration in human identity. Beyond the scientific and philosophical implications, the search for life on Proxima-B is also a reflection of humanity's innate curiosity and desire for discovery. Throughout history, humans have looked to the stars and imagined a future in which we explore and understand the universe. Space exploration is a natural extension of this desire, a quest to go beyond the limits of Earth and to answer questions that have haunted us for millennia. And the search for life on other planets represents a broader search for meaning. By seeking out signs of life in the universe, we are also searching for answers to the fundamental questions that shape human existence. Why are we here? What is the nature of life? How did we come to be? Proxima-B, as a potentially habitable planet, offers an opportunity to reflect on these questions. If life exists there, it would be a reminder that human life is part of a broader cosmic narrative, one that stretches across the universe and spans millions of years. Exploration of distant planets like Proxima-B also raises questions about human evolution and our future as a species. If life can exist on planets like Proxima-B, how will we, as humans, adapt to new environments and technological advances? Could future generations of humans one day live on Proxima-B or another exoplanet? What would it mean to create a new chapter in the human story, off-world, on a planet light years away from Earth? The answers to these questions are not just about science and technology. They are about human identity. The act of exploring other worlds and searching for life on those worlds is a reflection of humanity's quest for understanding and connection. It's a testament to our desire to explore the unknown, push the boundaries of possibility, and find meaning in the vast expanse of the universe. Proxima-B and the future of humanity. As we consider the implications of Proxima-B's potential to support life, we must also look ahead to the future of human space exploration. Proxima-B is one of many exoplanets that may one day become a target for human exploration. While a mission to Proxima-B is still far in the future, it represents the possibilities of interstellar travel and colonization. The ability to reach planets beyond our solar system would fundamentally alter the trajectory of human history, opening up new frontiers for exploration, survival, and even expansion beyond Earth. At the same time, this future is not without its challenges. The technology required to travel to Proxima-B is still in development, and the obstacles we face in creating habitable environments on distant worlds are immense. However, the pursuit of interstellar exploration represents a broader aspiration for humanity. A desire to find new worlds, to understand the universe, and to ensure the survival of our species in the face of cosmic uncertainty. The discovery of Proxima-B and the ongoing search for life beyond Earth forces us to confront our own limitations and consider how we, as a species, will adapt to the vast unknown. The quest to answer the question of whether life exists beyond Earth is not just about finding extraterrestrial organisms. It's about understanding ourselves and our place in the cosmos, asking whether we are truly unique in the universe, and whether we are ready to take the next step as explorers and stewards of the stars. Ethical considerations of exploring and colonizing Proxima. As humanity advances in its quest to explore the cosmos, the potential for colonizing other planets, such as Proxima-B, raises not only scientific and technological questions, but also ethical dilemmas. While the excitement of discovering life on other planets or the possibility of settling on an exoplanet is undeniable, it also brings to the forefront important concerns about planetary protection, resource exploitation, and the potential impact on extraterrestrial environments. These ethical challenges must be carefully considered as we continue our search for new worlds and dream of interstellar colonization. Planetary protection. Should we alter other worlds? One of the most pressing ethical issues surrounding the exploration of planets like Proxima-B is the question of planetary protection. As we send probes, rovers, and potentially even humans to distant exoplanets, we must consider the potential impact we could have on those environments. The question becomes, should we alter other worlds in any way, nor should we preserve them in their natural state? On Earth, we have a long history of environmental conservation efforts aimed at preserving ecosystems and protecting endangered species. When we consider exploring other planets, we must ask whether we should apply similar ethical considerations. If we were to colonize Proxima-B or any other exoplanet, would we be tampering with a pristine, untouched environment? What if microbial life exists there, even in its most rudimentary forms? How would we ensure that our presence does not destroy or irreversibly change any potential alien ecosystems? The planetary protection protocols established by organizations like NASA and the European Space Agency, ESA, are designed to prevent the contamination of other planets with Earth-based life forms. The purpose of these protocols is to ensure that we do not accidentally introduce Earth microbes to planets that could harbor their own forms of life. The ethical responsibility of avoiding contamination is paramount, and it extends beyond just microorganisms. If we were to establish a human colony on Proxima-B, we would need to ensure that we do not introduce foreign ecosystems that could disrupt any potential life on the planet. Terraforming or altering the environment to make it more Earth-like could have unintended consequences, potentially wiping out alien life or disrupting delicate planetary systems. At the same time, as we develop the technologies to reach distant worlds, we must also consider the ethics of terraforming and the potential for creating environments that might suit human habitation at the cost of alien ecosystems. While humanity might be motivated by the desire to expand and survive, this pursuit must be tempered with caution and respect for other worlds. The ethical considerations of terraforming and colonization are complex, as they ask us to consider whether it is right to change another planet's environment for our benefit, even if the planet is lifeless or potentially inhabited. Exploitation of resources. The ethics of mining and colonization. Another major ethical issue concerns the exploitation of resources on planets like Proxima-B. The discovery of a planet with potentially habitable conditions could open up a new chapter in human history, not just for exploration, but for exploitation. The resources available on Proxima-B, such as minerals, gases, and energy sources, could be seen as valuable assets for future human colonies. However, the ethical question arises: should we exploit the resources of other planets? Or should we preserve them as we would protect natural resources on Earth? In our own solar system, we have already begun to discuss the possibilities of mining asteroids and extracting valuable materials from celestial bodies. The idea of mining planets and moons in distant star systems like Proxima-B brings the same ethical dilemmas. Exploiting resources could be essential for the survival of human colonies in space, providing vital materials for construction, energy production, and life support systems. But the potential for environmental damage, depletion of resources, and the long-term effects on the planet's ecosystem should not be overlooked. Further complicating this issue is the concept of ownership. Who would own the resources of a distant planet like Proxima-B? Could one country, corporation, or international organization claim ownership of the planet's resources? As space exploration becomes more commercialized, questions of space law and property rights will need to be addressed. The ethical issues of ownership, exploitation, and fair distribution of resources will become increasingly important as we look to colonize other worlds. Human rights and social justice in space colonies. As we consider the possibility of establishing human colonies on Proxima-B or other exoplanets, we must also think about the ethical implications for the people who would live there. In the context of colonization, the question arises: what rights would colonists have? Would they be citizens of Earth or of Proxima-B? The potential for social inequality, resource allocation, and the well-being of colonists on another planet presents ethical challenges that we cannot ignore. One of the central ethical issues is human rights in a space colonization context. If people are sent to live on Proxima-B, what protections will they have? Will they be subject to the same rights and laws as people on Earth? In the early stages of colonization, a pioneering group might be sent to establish the first colony. But what happens when a larger population arrives? Will there be laws to govern the actions of the colonists, especially in a harsh, isolated environment? Social justice concerns will also arise, particularly regarding the access to resources, healthcare, and education. Without careful planning and attention to human rights, space colonies could quickly devolve into oppressive societies where power and wealth are concentrated in the hands of a few, leaving the majority of settlers at the mercy of exploitative systems. The ethical responsibility of future generations. As we look to the future of space exploration and the potential colonization of planets like Proxima-B, we must also consider the ethical responsibility we bear to future generations. As we expand into space, it's crucial that we do so with a sense of stewardship. While the goal of reaching new worlds is exciting, we must take steps to ensure that our activities in space do not create harm, whether to the planets we explore or to the people who will one day live there. Future generations of humans will inherit the legacy of the decisions we make today. Will we build a future where space exploration is a force for positive change? Or will we repeat the mistakes of the past, where colonization and exploitation took precedence over careful, sustainable development. The way we approach Proxima-B and other planets in the future will set the tone for humanity's long-term relationship with the cosmos. Conclusion: navigating the ethical frontier. As we continue our search for life beyond Earth, we must remember that the exploration and potential colonization of planets like Proxima-B are not just scientific challenges. They are moral and ethical questions. The decisions we make today will shape the future of humanity in space. It is up to us to approach these decisions with wisdom, foresight, and a deep sense of responsibility for the planets we explore and the life we find or create there. The ethical considerations of planetary protection, resource exploitation, human rights, and environmental preservation will shape the future of space exploration. As we move forward, the conversations we have today will determine the type of legacy we leave for future generations. The ethical frontier of space exploration is as vast as the stars themselves, and it is up to us to navigate it thoughtfully, ensuring that humanity's reach into the cosmos is as responsible as it is inspiring.